Hey, Nick. Oh, your name tag is on the speaker set. I'll get you your name tag is on the speaker list. I'll get it to you later. Hey. Oh, great. Yeah. Photos where? It's fine with me. Yeah. Can we? Okay, everyone. We're going to start in about 5 minutes. So if everybody could grab their seats, or actually in 3 minutes. Ken. What is going on? All right, so we're going to get started. So if everybody could grab their seats, we'll get the show on the road. We have a fully packed day, so everybody can grab their seats and we can get started. All right, so let's do this. Okay, so welcome to the 4th Stanford BlockChain Conference. It's been a lot of fun running this conference for a couple of years now. I guess before we get started, there are just a couple of quick administrative things I wanted to say. First of all, if you want to get on the Wi-Fi network, just go to the the Stanford Wi-Fi network. There's Stanford and Stanford Visitor, so you can go to the Stanford one. And then just click on, I think, sponsored account or whatever it's called, and then you can log in using a very secure username and password, username blockchain and password blockchain, and that'll get you on to the Stanford network. Alternatively, you can also log into the Stanford Stanford Visitor network if you'd like. So either one would work. Now the entire event for the 3 days. It's going to be live streamed. The live stream links are on the program website, so you can see them there too. But if for some reason, I guess you're here, so you don't really need the live stream. But if for some reason you were here and you still wanted to watch the live stream, you can do that too. If you wanna tweet about the conference or things that are being said, there's a hashtag for it. And finally, there's also a Telegram group. All of this is up on the website, so you can get all this information there as well. The last thing that we may have forgotten to tell you, which is really important, is if you're driving onto campus and you need parking, there's a parking lot right across the street from here. Maybe today you guys already paid, but actually for tomorrow and for Friday, there's a parking code. Just use 6162, and parking is on us. So yeah, maybe just remember that for the following days. Okay, so let's see. So what this conference is about is basically bringing together two communities, sort of the practitioners who actually run various blockchain projects and academics who work on, well, fascinating research questions in the area. We try to make this a technical conference, yeah, so all the talks are about the technology of blockchains, yeah, so we want it to be, it's not about other aspects of blockchains. This is specifically about the technology. Yeah, so we're looking to discuss things like new ideas and research challenges. Obviously, researchers like me get excited about new questions. So if the speakers have interesting questions for the community that maybe they'd like people to think about, please mention that during the talks. And as I said, the goal is to kind of bring together the people who actually work in the area and the academics who think about problems in the space. Now, I can tell you this conference got a lot of registrations. So we have 1,400 people registered, which is kind of remarkable. So I'll hope they'll well, actually, if they all come here, if they all come in person, we're going to have some interesting times. But I can tell you that actually, given the number of registrants, we actually tried to get the Stanford football stadium for this conference, but unfortunately, they wouldn't let us. Yeah, so we had to settle for this beautiful facility. But given that it's going to be so crowded, we are going to ask people to first of all try to squeeze in. So as the day goes by, there are going to be more and more people coming in. So we're going to have to kind of share the space. Also, the other thing is there's overflow space at the other end of the building. So the whole building is ours for the whole 3 days. And what we have is kind of streaming going on to the other end. There'll be big TV screens, so you can watch everything that's happening here. In fact, it's much more comfortable to sit over there because there are tables and there's power. So for those of you who want to sit and watch the conference in more comfort, you can go to the other side of the building. It's literally just kind of on the other end. It's pretty close. Great. Oh, and then the other thing is if you want to talk, maybe try not to talk at the far end of the room. Maybe just take the conversation outside. It'll help the speakers and the audience focus on what's being said. All right, so with that, let me say that the program itself is organized by myself, Benedict Boons, who's right here, and Byron Gibson. So actually, round of applause to Benedict and Byron for helping make this happen. Thank you. Yeah, we had 118 submissions. I wish we could accept all of them. There were fantastic submissions that we really, really enjoyed reading, and I wish they could be presented here. But unfortunately, we only had room for 25 presentations, so we ended up accepting 25, and then we also have 7 invited talks in the program. However, if you still want to speak, then tomorrow, actually, we're going to have a lightning talks session. So this is going to be tomorrow at noon. So anyone can come and speak for 2 minutes about whatever topic you like. Even if you have a job opening that you'd like to advertise, anyone is very welcome to speak. The only thing that we ask is there's a bit of interest in this session, and so what we ask is please go to the program page, cbr.stanford.edu/SBC20. Go to the program page, and if you look at this session, there's a link here to sign up to speak at the lightning talk, and just submit a talk proposal. If you want slides, you can submit slides, and then those will be presented during your 2-minute presentation. So depending on how many submissions we'll get, we may have to downsample, but I hope that we can accommodate everybody. Okay, so that's the lightning talk. So think if you want to say anything during the lightning talks, and go ahead and submit a proposal. Let's see. So the program itself was selected by the program committee. So we had a very large program committee to help select from this large number of papers that were submitted. So they did a lot of work to help us make all this possible. So again, a round of applause for the program committee, please. And thank you all. Thank you all for all the work. We hope you'll do it again next year. Similarly, the reason we're able to run such a large conference, and you noticed the registration is free. Yes, everything is free here. So the reason we're able to do that is because we're very fortunate to have fantastic sponsors for the research program and for the conference. So, in fact, the Center for Blockchain Research is funded by Ethereum Foundation, Protocol Labs, Interchange, Omisago, Definity, and Polychain. And then we had a couple more folks, Consensus, Lemniscape, and Calibra, who contributed specifically to the conference. So again, thank you so much for all this contribution. This is exactly why we're able to run this conference and keep it free and open for everyone to attend. So thank you all for your support. Yep. Now, I figured I'd be a good host and just tell you a little bit about, if this is your first time on campus, I can tell you this is a beautiful campus. Maybe during the breaks, you'd like to walk around and see some of the sites. There's a lot to see, so I'll just walk through a few highlights. So we're over here. Yeah, so this is kind of Campus Drive. The parking lot is way over here, but this is kind of where we're located on campus. If you just walk sort of across the oval, sort of in that direction, there is a Rodin Sculpture Garden, which is like the largest Rodin exhibit outside of Paris. So if you want to see art and a museum, it's all it's kind of a nice walk, and you can see you can stroll over there during lunch. Let's see, what do we have here? If you want to go up the Hoover Tower, that's open to the public. You can go up. There's a beautiful view up there. Sort of you can see the kind of the whole computer revolution happened within a 5-mile radius of this tower. There's a bookstore not too far away too if you want to browse books or such. And just so you know where we live, this is where the computer science department is. This is where we spend all of our time. It's kind of on the other side of campus. So that's it. Those are the highlights for the campus. So you can walk around and enjoy the sites. I guess this talk wouldn't be complete without saying that we also run a monthly seminar. Everybody's welcome to attend. We have a whole bunch of courses on blockchains that are available remotely too, if you guys want to participate. And finally, there's even a Stanford BlockChain Club for undergraduates. They're helping actually with the administration back there. So I wanted to just give them a shout out and thank them for all the activities that they're doing. Okay, good. So the schedule for the coming days, we're going to run from 9 to 5. The program's going to run from 9 to 5. At lunch, we're going to have lunch at around 12:30. Lunch is going to be served basically out here. So you can literally just walk outside, grab your lunch, and mingle. So it should be a fun time, or you can walk around campus. But there'll be lots of space for people to mingle during lunch, so it should be a fun opportunity to talk to folks and meet folks. And then tonight we're going to have a reception. Starts at 5:20, so just hang around here. The reception will be right outside the lecture hall, and there'll be hors d'oeuvres and such. Again, just opportunity for folks to talk to one another. Then dinner Thursday, Friday, you're on your own. There's lots of opportunities to eat dinner in Palo Alto. And as I mentioned, the lightning talks are tomorrow at noon. Now, last note, the Alumni Center people asked me to just remind everybody, there's overflow sitting on the other side of the conference structure, so please go there if you want tables and power. They asked us to remind folks that there's no smoking close to the building. And finally, given the flu season, maybe you've heard that there's some virus going around, we put hand sanitizers around the whole room so everybody can use them at their pleasure. And then there are also masks available at the front desk. If anybody wants a mask, we'll just give them away for free. Okay, so that's all I had. So enjoy the conference. And with that, I'm going to hand it over to our first session chair, Ariel. So please come up. Ariel, thank you all. Yeah, and I'm looking forward to all the talks. So all yours.
Right. So we first have Stefan Jambowski from Warsaw University about limits of plasma.
Thanks.
Okay, so thank you. So the title of my talk is Exploring the Limits of Plasma. It's a joint work from with Grzegorz Fabiański, Sebastian Faust, and Siavash Riahi from the TU Darmstadt. So let me start with telling you a little bit what plasma is. So plasma is, roughly speaking, a family of layer 2 solutions for scaling blockchain. It was proposed in 2017 by Poon and Buterin. And as I said, it's a family of protocols, so there are plenty of different plasmas. And this is like a world map of plasma from, I think, more than a year ago. So several things are already missing there. So it looks a little bit, so it's a very active area, a little bit chaotic. Another name for this area is called commit chains. Okay, this was proposed recently. So what is our result informally? So our goal in general was to bring some order to this plasma efforts. And we started proving lower bounds. So our result informally is we prove that every plasma system must either have large exits, like plasma cache, or it must suffer from a variant of mass exit problem caused by data unavailability. Okay? I'm going to explain you a little bit more what it means on the next slides. The paper is available online on ePrint. So in some sense, there were these two approaches to doing plasma cache and plasma MVP. They both have some advantages. We showed that you cannot have the best of the two worlds. Okay, so let me start with telling you how plasma works. So plasma can be thought of as a bank on the blockchain. Okay, so you have a bank where you have like the operator of the bank, and you have people who have some coins or tokens in this bank, and it is secured by blockchain. Okay, so there is say Ethereum blockchain in the background that is securing the operations. And yeah, there's a plasma smart contract on the blockchain that will be used to guarantee the security so that no money can be stolen. So the blockchain is often referred to as main chain. Okay? So this is like the main chain, and then you have like a plasma chain. This will be something that will be virtual. And since it's a bank, then the users can do things like add more tokens to the bank, to the account, or withdraw some tokens from their accounts, or transfer tokens between each other. Okay, so it should work like a bank. Main idea, design idea is, as I said, there is the operator and the plasma contract on the main chain. The operator maintains kind of like a virtual ledger, so call it plasma chain or plasma ledger, and he publishes this plasma ledger off-chain, so he publishes it on his web page, for example, and he periodically hashes the contents of this plasma ledger on the main chain. Okay? So he uses some hash function to hash it, and goes in periods, say epochs, that take 1 hour or more. Okay? So once per hour, the operator will hash everything and put it on the blockchain. So these things that happen on the operator's web page, they are called off-chain operations. And then you have on-chain, so publishing hashes. Okay? So of course, the savings here are quite obvious. If you want to make lots of transactions between the users, they don't have to put them all on-chain. They just do it virtually on the operator's web page, and the security is guaranteed by the fact that things are hashed. Okay? And it should tolerate security against, it should provide security against arbitrary corruptions. Okay? Even corrupt operator cannot steal the money. So some more details. So you have the operator and every user, and you have this plasma ledger L. So the operator will hash the plasma ledger on the main chain, and he uses typically Merkle hashes for this. So Merkle hashes are used because then every user can efficiently prove that his account or whatever was hashed into the was put on the main chain, and it is required that every user constantly monitors the situation and provides some checks. Okay, so what he has to check is he has to check if the plasma ledger was published off-chain. Okay, so he has to monitor the web page of the operator constantly to check if things are published. He has to check if what is published agrees with what was published on-chain, so he has to check the hashes. And he has to check if the ledger is syntactically correct. Okay, so if everything is okay there. And if it doesn't hold, then the user concludes that the operator is corrupt and takes some actions. Okay? So it's like the responsibility of the user to watch if everything is okay. So if you look at these checks again, then there is a problem. Okay? So these are the checks from the previous slide, 1 to 3. So these things, 2 and 3, are objective. Okay? So if the hash is computed incorrectly or the ledger is not syntactically correct, I can prove it somehow to the contract that the operator is cheating. Okay? The bigger problem is with the first thing, namely checking if L was published at all off-chain. Okay? Why? Because it is subjective. Okay? It's not it cannot be proven or refuted on the smart contract if something was published off-chain, okay? Because it's something that concerns the internet, something that concerns the fact whether something appeared on the web page of the operator. And that's called data unavailability attack. Okay? So the data unavailability attack happens when the operator publishes the hash on-chain but doesn't publish the corresponding L. Okay? So we don't know what was hashed. And as I told you, the biggest problem is that it's subjective. Okay? Some people can have an opinion that it was published, and some others can think that it was not published. So how to react to this data unavailability problem? The simplest solution is just escape the system. Okay? Take your money and run. So if I conclude that there is data unavailability, I just withdraw all my coins, and I say I use age that was the last age that was explained correctly. Okay? The last age I was aware of. So what are the problems? So as I told you, data unavailability is subjective. Okay? So it's not clear who should pay the fees. Okay? So if I'm escaping with all my money, it costs, and then the question is who should pay the fees. This is an example of something called non-uniquely attributable fault. Okay? So that's something where the smart contract cannot determine who is corrupt. Okay? So either the user is honest and the operator is corrupt, or the user is corrupt and the operator is honest, and both things are equally likely from the point of view of the smart contract. And another problem is that if there is a real data unavailability there, then you have a situation that's called mass exit. Okay? So everybody tries to exit at once. There's one moment when lots of people try to exit. And these mass exits are particularly problematic in real life because, well, so they can cause blockchain congestion, or moreover, it can happen that a malicious operator starts to do these things when there is a blockchain congestion, right? So, this was observed by many people that in real life this is a problem. I mean, this may be a problem. And the question is, can we have Plasma that doesn't have this issue of mass exits caused by data unavailability? And the answer is, luckily, yes, there is an answer to this, and it's called Plasma Cache. And Plasma Cache is a special kind of Plasma where it's more based on like tokens than on users. Okay, so you have a concept of tokens that have owners, and they are not divisible, they cannot be merged or divided. Okay? Think of them as some game items. Okay? So every game item has some owner, it's like a particular distinguishable game item. Nice thing about Plasma Cache is that it has no mass exits caused by data unavailability, it has non-uniquely attributable faults. How is it possible? Because as I told you, every token has an owner. Okay? So each user has to protect only his own tokens. So for example, this user thinks these are his tokens, this user thinks these are his tokens. And this allows us to get rid of this problem, because the only thing I have to do is I have to watch if my tokens are not leaving the Plasma chain. And for this reason, it's called non-fungible Plasma. Okay? So it's very important, this non-fungibility thing, that things cannot be merged or divided. And the normal Plasma can be called fungible Plasma. Okay? So Plasma doesn't have this restriction. This comes at a price, and the price is that the normal exit size in Plasma Cache is linear in the number of tokens that I'm withdrawing. Okay? So the amount of data that I have to put on the blockchain when I'm just exiting the system is linear in the amount of money that I have, even when everyone is honest. So if I have some tokens, say I'm this user and I have 5 tokens, then what I have to put on-chain are exactly these 5 tokens. Okay? So it's like linear in how much money I have. And the consequence of this is that Plasma Cache cannot be converted to a fungible Plasma by using very small denominations. Okay? So we could think, okay, maybe it's like an artificial distinction, because maybe we could have fungible Plasma out of Plasma Cache by saying that every token is worth 1 Satoshi, for example, right? But this cannot be done, because then you would have like huge exits. Right? Okay, so we have this distinction between Plasma Cache and fungible Plasma. Plasma Cache has large exit size under normal circumstances, but doesn't have, sorry, I think it should be the opposite, doesn't have mass exits, and fungible Plasma has short exits and has mass exits. Yes. And there are examples of like implementations of both things. So there's Plasma cache was implemented by Loom network. Then you have different variants of Fungible Plasma implemented by different companies. A natural question is if it's inherent. Okay, so can we have Plasma that has both features? So it has no must exits caused by data unavailability, and it has small exit size. And the main message of our paper is negative, that you cannot have it. And actually, in the recent months, there were many reports about Ethereum community kind of abandoning a little bit this Plasma idea. And my understanding is that one of these things is that they couldn't come up with like Fungible Plasma with short exits and no mass exits. Okay? And this results kind of confirms that this was not because they couldn't come up with a good idea. It's something inherent. Okay, so let me tell you more about the technical part of the paper. So some terminology. So an attack on Plasma, in our terminology, is a strategy for the adversary that takes the full control over corrupt users. So some users are corrupt and the adversary controls them. And you have a scenario on how the honest users behave. Okay, so this is also part of the attack. This is modeled in theoretical language using the concept of environment. And you have must force on-chain action, a situation when honest users need to quickly send a lot of data to the blockchain, even when they didn't want to exit. This is slightly more general than must exit, because you can have like theoretical artificial cases where people don't, strictly speaking, exit the system, but anyway, they have to touch the blockchain. And our result, in simplified form, is that for every Plasma pi, one of the following holds. Either you have an attack on this Plasma pi that causes must force on-chain action, and moreover, it has non-uniquely attributable faults, or there exists an attack on Plasma that causes exit size to be large. Okay? By attack, I mean some kind of like scenario how the users would transfer money between each other. And in other words, there is an inherent separation between Plasma cache and Fungible Plasma. You cannot have the best of the two worlds. Okay, and the main proof idea is we show that if 1 doesn't hold and 2 doesn't hold, then you can compress long random string into a short string. Okay, so you can do the following. So let me give you some notation. You have users will be denoted by U1 to the UN. You can have the following. You choose a random subset of users, starting from U2. This will be a technicality on the next slide. And you can compress this description of a random set into something shorter that we denote tau. Tau that's much shorter than n, such that later you can decompress this thing tau back into V. Okay? So this is a contradiction. Obviously, you cannot compress long random strings into something shorter. So to this end, we construct an attack. This attack consists of 2 epochs. Epochs, I told you, are these moments where people, like time between the commits on the main chain. In epoch 1, we choose a random subset V of users. And in this moment, we'll launch data unavailability attack. On epoch 2, the users will try to exit. And here we'll do active corruption of some parties. And we prove that if Plasma is secure, then the set of users who do not manage to exit has to be equal to V. And then we show that if it's 1 and 2 hold, then you can compress V into a small string. Okay, so how does epoch 1 look? So you have the operator, you have user U1, and you have some other users, and you have the main chain. Okay? At the beginning, we give 1 token to every user except of U1. Okay? And then we choose a random set V, which is a subset of all users except of U1. Okay? And then in the first epoch, the users from set V transfer their coins to user U1. Okay? And at the same time, we isolate the rest of the users from the operator. Okay? So this is the data unavailability attack. We don't explain things to these guys. Okay? And now we let U1 exit with all the tokens on the main chain. Okay? So there is some exit. Denote this exit, so the transcript of messages communicated to the main chain as T0. These guys most likely will protest, right? Because they are isolated from the operator. They see that something was published on the main chain was not explained. So they are going to send some messages T2 to the main chain. And actually, these guys can also send something because maybe they are, by the protocol, they are triggered to react. Okay? So this is denoted by T1. Okay? So you have T0, T1, T2. These are like transcripts of messages sent by the users. I'm simplifying things a bit. In the paper, it's a little bit more complicated, but this is roughly the main idea. Okay? So now we have an observation. If we want short exits, then this T0 has to be small, right? Because of the definition of short exits. If we don't want to have large non-uniquely attributable forced on-chain actions, then T1 and T2 have to be small, right? Because these were users that were not, they didn't want to exit the system, okay? So they should have small communication. So recall that these were the messages sent to the blockchain by users V, and these were messages sent by the other users. So if we want to have both of the above properties, then all these things have to be small, okay? All the transcript messages that were sent have to be small. Okay, so now we have Epoch 2, and Epoch 2, we corrupt users from the set V, and we switch off completely the operator and the user U1. U1 already exited, so he's not important anyway. And now we let the guy from here pretend that they were isolated and also exit with one token, okay? So they we do it by a technique called rewinding. Okay? So we have to rewind back to the state from when everything started, and we say, okay, pretend that you were also isolated, okay? and escape. And these guys are honest. We just tell them, okay, exit with your one coin. Okay? So these guys are kind of exiting the main chain, exiting the plasma chain illegally. These are exiting legally. Okay, and now let's look at the set of users that did not manage to exit. Okay? Did not manage to exit. So who did not manage to exit? So for sure, the honest users, they should be able to exit with their coins, right? Because they were just behaving honestly, right? So they should be able to exit. And none of these guys should be allowed to exit because they already escaped with their coins before, right? So that would be allowed, sorry, they didn't escape, they transferred to U1, right? So they don't have this coin. Okay? So the set of users that didn't manage to exit should be exactly the set V. Okay? So how to compress a set V? We apply this to epochs. Okay? So we have the first epoch where we plug in V in the first epoch. Okay? We look at the transcript T0, T1, T2 that was stored, and we decompress. To decompress, we apply the second epoch, and we look at the users who managed to exit. Okay? And we know that V prime is equal to V. This T0, T1, T2 should be here. T2 is small, so we obtain a contradiction. We manage to compress things into. Okay, so in reality, proof is a little bit more complicated. As I told you, we have actually 4 transcripts, not 3. Yeah, for the details and the concrete parameters, you can check the paper. There is a generalization. Our results also covers plasma when you have like additional collateral on the operator that can be used to compensate the fact that the operator is dishonest. Okay, so our conclusion is that there are good theoretical reasons why the practical community came with these 2 types of plasma. There are some ways to get around of this. So there is this defragmentation technique suggested by Vitalik. It doesn't. So this is the defragmentation technique where you have you kind of had an approach of plasma cache, and then you kind of try to merge the coins. And it works assuming that some users are cooperating with each other. So it has some additional assumptions that we don't have in our paper. So this is one way to get around this impossibility result. Then we have roll-ups. Okay, this is yet another technique, very popular in the last year, I think. I guess one of the reasons why people started to investigate roll-ups is that they realized that plasma has some limitations. So this is kind of confirmation of this in our paper. And then another approach is to have some kind of semi-trusted committee that certifies if data was available or not. Okay, so you can have like voting whether, like outside of blockchain, if data was made available by the operator or not. I think this is what StarkDex uses. And I think more work on formalization and extensions of plasma is definitely needed in this area. Okay, thanks. That's it.
So what do you think, right, in terms of maybe your personal taste, or also what do you think is right now the best trade-offs, layer 2 or scaling solution, blockchain solution?
Well, the best one is like off-chain channels that we are working on. No, but from this family, I don't know. I think so this Starkdeck solution definitely makes sense, right? Rollups also makes sense. I think like the next thing I want to look at in terms of research is like to understand this rollups things. I think research-wise, rollups are interesting because this committee for data unavailability is a nice solution, but it's like kind of like straightforward solution. I think rollups are interesting to investigate.
So I think do you have a microphone for the question? All right. So maybe while you ask your question, the second speaker can set up.
Don't hear you. I don't hear you. Yes.
Check.
Yes.
Thank you. How do you determine the V prime group? Now that we have like a V, can you explain a little bit about the V prime?
Yeah, so basically what you do is you run an experiment where you revert the dishonest people to the initial state. So basically, okay, this is a good question because basically to make this compression argument valid, we cannot assume that we know who is corrupt or not, right? Because then we would not compress anything. So we kind of revert every user in the system to the first stage, like when everything started, when they all had one coin, and then we just run them, assuming that there was no data unavailability attack. Sorry, assuming that basically they were the guys that they were not withdrawing coins. So we just run the experiment and we see how it goes.
Okay, we have time for one more, if there's. All right, let's thank Stefan again. And next we have Ed Felton from Off-Chain Labs to talk about off-chain contracts with online security, faster off-chain contracts with on-chain security.
Thanks. Good morning, everybody. I want to talk about the latest version of our Arbitrum system. The first version of Arbitrum was discussed in a paper in Unix Security 2018. What's changed since then is a bunch of advances in the technology, as well as the construction of a real running system. This is the first working roll-up system for general smart contracts. So I want to talk first. I'll set the scene to provide some context on what we're talking about and how what we're doing fits into the larger picture. Then I'll talk about how the system works, what has changed since the previous paper, and some lessons that we learned from building and deploying it. Okay, so first, let's talk about layer 2 systems that support smart contracts. These systems generally rely on having a set of parties who I'll call validators, who are responsible for tracking the state of the L2 chain and its contracts and taking action to make sure that the L2 chain develops correctly. So we can build a kind of taxonomy of these systems. I'll start by with what the assumption is about how many validators you trust. Over on the left, we have systems where you trust K out of N validators. K is usually 2/3 of the validators plus 1. This would be the case for, say, a BFT-based system. These are consensus systems that decide what to do based on who says what. On the right, we have systems where you only assume that one of N validators is honest. And these are systems which allow one validator who's correct to win out over n-1 who are malicious or incorrect. And so these systems necessarily have to involve some L1 adjudication of what's actually true, as opposed to a consensus system, which is more like voting. So we're going to be on the right-hand side with a 1 out of n assumption. So a very favorable trust assumption for the developer and the user. Now the next branch here is whether we have a fixed validator set or a situation where anyone is allowed to act as a validator. When anyone can be a validator, that's typically called a roll-up protocol. And I'll go in a little bit more into what roll-up is and why it works a little bit later. The alternative is to have a fixed validator set so that at least at any given point in time, there's a single enumerated set of validators. And within that subset, the most popular and best known type is a state channel approach. In a state channel approach, basically you operate entirely off-chain, and if all of the validators agree unanimously on what should happen, they can agree off-chain, they all mutually sign it, and you can move on. And only at the end of the period of agreement do you have to take the receipt, the mutually signed receipt from that whole chain of updates and cash it out on chain. So the good news in state channels is it's incredibly efficient when everyone is agreeing and participating. But if any validator stops agreeing or stops participating, in classic state channels, you have to fall back to doing everything on the main chain. And that's a substantial problem in practice. In our 2018 paper, we introduced Arbitrum channels, which is an approach that is a kind of hybrid of the two, where you have a fixed set of validators, and everyone, when all those validators are operating by unanimous agreement, you operate off-chain just like a state channel. But when you stop getting unanimity, then instead of falling back to on-chain, you fall back to a permissioned version of the roll-up protocol. So this gives you kind of the best of both worlds. You get the efficiency of a channel when it's available, and you get the much better than L1 efficiency of a roll-up system when you don't have unanimity. Okay, so I'm going to be talking in this talk about the yellow area down here on the right, about the roll-up part of the protocol, which is the most interesting and complex part of the Arbitrum channels protocol, but then that's also incorporated into Arbitrum channels as well. Okay, let me drill down a little bit more into how a system like ours and many of the similar ones work. So you have some amount of source code which represents the smart contracts that some developer wants to run. That might be some legacy Solidity code, or it might be something else. You're going to take that source code and run it through a compiler, in our case a custom compiler, and that's going to generate an executable program to run on some kind of virtual machine which the L2 system is implementing. So once you have that executable, which is suitable for running at L2, then you can launch your chain by launching a set of validators. Each validator has in it an emulator for the VM so that it can emulate VM programs in that VM architecture. You take the compiled program and you run it on that virtual machine. Now, if all's going well and all the validators are honest, then all the honest validators will have equivalent replicas of the state of that virtual machine as it runs. Dishonest validators will do what they do, but honest validators, if the protocol is correct, will always agree and have exact replicas of what the state is. Those validators ideally agree and make progress quickly, but if they don't, then they're going to interact with an on-chain manager, which is a small contract that sits on the underlying L1 chain, in our case Ethereum, and talks to the main chain, and it's responsible for the ultimate adjudication of any disagreement between the validators. And of course, the special sauce in any protocol like this is how you can make the job of that on-chain manager as small and fast and efficient as possible, while still giving the security guarantee that you need and the generality of smart contracts. But this is the basic picture. Okay, so let me talk a little bit about the design of our system. First, goals. Our first goal was to run general purpose code or contracts. We want to make it fast and cheap, even if we're on a slow and expensive layer 1. We want to provide strong guarantees of security. In particular, we want to provide in an antitrust fashion guarantees of safety, liveness, and finality. So by antitrust, what I mean is that any one party acting alone can ensure that that property holds. Safety means that no bad state change will occur. Safety means no bad thing will happen. Liveness means that some good thing will eventually happen, or something will eventually happen, which combines with safety means some good thing will eventually happen. And finality means that if a valid state change is proposed and becomes pending on chain, that it will eventually be confirmed. And this will allow parties to treat things as fated to be confirmed even before they're actually confirmed by the protocol. And that allows faster response time in practice for a lot of for users. We want to interoperate with the layer 1 chain, meaning that you can make calls back and forth between L1 and L2 contracts. You can move the underlying token like ETH on Ethereum or other tokens back and forth easily. And we want it to be censorship resistant so that it has the same censorship resistance properties as the underlying L1 chain. The approach that we took in building this is, first of all, we did obvious stuff, try to minimize the on-chain work, try to go fast. Everybody does that. But in particular, I want to point to 4 things that we did that perhaps are distinctive. First, we focused on running many L2 chains rather than just a single L2 chain to rule them all. We believe it's better to have per application or per sector L2 chains. Having more L2 chains gives you more parallelism, so you can go faster in aggregate. It also offers better incentives with respect to who's going to be a validator and who's going to pay for a chain. If the application you care about is mushed together with 10 other applications on the same chain, then if you validate that chain, you're validating the thing you care about, but you're also validating the work of 10 other things you don't care about. So by putting the things that have coherent communities of interest onto a chain by themselves, you have a better incentive structure than if you had a single large chain. We have many chains, but on each chain we run a single virtual machine instance. We don't have separate virtual machines per contract or per user or anything like that. We think there are big benefits to taking all of the activities on one chain and running them within a single program. That means we need to compile together all of the separate contracts and libraries that make up that might be running on a chain. It also means we need to have a runtime system which is built into that program, which is able to do bookkeeping, scheduling, dispatching, check signatures, check formats, and various other things that you would do in a runtime system or operating system on a conventional machine. And the role of that runtime system is very important both for efficiency and for correctness. One of the lessons I'll come back to later is that having that runtime system is a big benefit. We want to create incentives to the validators to stay in the fastest mode. And then finally, we pay attention to the safe speed limit. By the safe speed limit, what I mean is that is the speed at which you can allow activity to happen without outrunning the ability of validators to keep up. Validators need to be able to check on and ensure the correctness of everything that happens. And it's possible to propose stuff faster than the validators can check it. Ultimately, the speed limit in your system, the safe speed limit, comes from how fast can validators check stuff out. And so we designed the system to make sure that the validators could always run at full speed checking things out. Okay, so this boils down to, in the real design, two use cases and 2 protocols. There's the Arbitrum rollup protocol, in which anyone can be a validator. As in any rollup protocol, if you want to make good on that promise that anyone can be a validator, anyone needs to be able to get the information they would need to be a validator. And that means that they need to be able to go on the main chain and find enough information to bring themselves up to date so they can start validating. It also means that if somebody gives them a recent checkpoint of the state of the system, that there's enough information on chain to verify that checkpoint so they can then move forward. And in the rollup protocol, we used an approach based on people making proposals, those proposals being challengeable, and if there is a challenge, there'll be a dispute. I'm going to dig into how this works in a bunch of detail in a couple minutes. In the channel protocol, as I said before, you have an enumerated set of validators. You can maintain privacy so that only the validators know the internals of what's happening inside your chain. When all the validators are cooperating, you go very fast, entirely off-chain, just like a state channel. But when they're not, you fall back onto a permissioned version of the rollup protocol. Okay, with that background, let me now dive into 2 aspects of the real system and protocol. I'll talk first about how the rollup protocol works at a fundamental level, how you can resist delay attacks by using a branch and prune approach to managing the state of the roll-up chain. And then I'll talk about this interesting issue that arises about how to handle time, messages, and interoperability when you're in an L2 setting. Okay, so first, the roll-up protocol. So one of the key notions here is what we call an assertion and what some other systems might call a roll-up block. This is a claim about the execution of the virtual machine in the chain. And that claim might cover the execution of many transactions of work. So any validator can post an on-chain assertion, which is a claim about what the chain will do or has done. And it consists of these things. First, it consists of a set of messages that the chain is consuming from the head of its inbox in doing this. These messages are things like requests to the contracts to execute transactions or incoming transfers of currency. The assertion contains a number of steps that allegedly can be executed by the chain's virtual machine. It includes a root hash of the state of the machine after those steps have been executed. The entire machine is organized in a kind of Merkle tree, so you can summarize its state in a single hash. And the assertion also asserts a set of outputs that are allegedly produced by the execution of those steps. Those outputs are things like log items, events, and payments that are made by those contracts. The Arbitrum protocol is going to decide, after an assertion is proposed, whether it's correct or not. It will either accept it or reject it ultimately. All right, now let's talk about how that works. So let's start, and I want to talk about this notion of the state tree, which is fundamental to the execution of the protocol. So I'm going to start my story in this state. You can imagine, in this situation, you can imagine that the history of this chain extends way off to the left. There's a long history back to some Genesis state. And I'm showing just the last 3 states in the history here. And I've painted them green because these states have been fully confirmed by the protocol. They're accepted. They have definitely happened. And the on-chain contract keeps track of the hash of the latest confirmed state. That is the latest thing that the chain has decided has definitely happened. Now, Alice is a validator. She wants to propose an assertion about what this chain will do next. So Alice posts an on-chain transaction proposing her assertion. That then forks the state of possible futures. There are now 2 possible futures, one in which Alice's assertion is accepted and one in which it's rejected. And the system is ultimately going to choose to go up or to go down at this branch point. Now, when Alice makes the assertion, she has to stake on that assertion. She has to put down a monetary stake on the state in which her assertion is accepted. When she puts down that stake, she is claiming that that state will eventually be confirmed. And the rules of the protocol say that if and when that state is confirmed, Alice can get her stake back. But if that state is ultimately rejected, Alice will lose her stake and it will go somewhere else. So Alice has staked. Once she has staked, a challenge period begins. A timer starts, and every other validator has some length of time in which to check out Alice's assertion, decide whether it's right, and then, if it's wrong, to challenge it. So everybody else starts checking out Alice's assertion. Bob checks it out, decides it's correct. Now, Bob can optionally choose to also stake on that same node, or not. But in this story I'm telling you, Bob has staked on that node. He puts down a stake, and the rules of his stake are the same. If that node is confirmed, he'll get his stake back. If not, he'll lose his stake. So one thing that can happen is Alice and Bob are staked like this, the deadline runs out, and now nobody else can stake for or against that assertion anymore. Now the system looks at this, it says everyone who has staked is staked on the same branch. Therefore, we have unanimous agreement among those who chose to speak, and so we're going to go ahead and confirm that node. Now the top node will be confirmed, it will turn green, Alice and Bob can get their stakes back, and time moves on. That's one thing that can happen. Another thing that can happen, though, is that Charlie can stake on the state where Alice's assertion is rejected. Now we have a disagreement between Alice and Bob on one hand and Charlie on the other hand. And so the system is going to put Alice and Charlie into a dispute. They then execute an efficient dispute resolution protocol that was described in our previous paper, which involves an interactive protocol where they use bisection to narrow the scope of the dispute down to a dispute about the execution of a single instruction, and then the on-chain component evaluates that single instruction. So that dispute goes on. When the dispute ends, in this case, Alice will win because she's right, Charlie's wrong. Alice is therefore able to win the dispute. When Charlie loses the dispute, he loses his stake. Half the stake goes to Alice, the other half gets burned, and Charlie gets booted off of this diagram. He's no longer staked. Now the system is again in a state where everyone who is staked on the positive side, and the system will then immediately accept Alice's assertion is correct, and that top state will turn green. Okay, now that's all well and good, but what happens while that challenge interval is running? We'd like to be able to pipeline these assertions. And so the way pipelining works is basically while Alice's assertion is under consideration, Bob can make another assertion on top of Alice's. In fact, he can pick any leaf of this tree and make an assertion from that leaf, which will cause 2 nodes to sprout off the bottom of that leaf. So here Bob has chosen to build on Alice's assertion. And now Bob has to stake on the valid branch for the assertion that he made. But notice that by staking on that state, he's also implicitly staking on the correctness of Alice's assertion, because Bob's state cannot be confirmed unless Alice's is also confirmed first. So Bob is allowed to move his stake to the right because he's not undoing any commitments that he's made before. He's only committing to more stuff. Any staker can always move their stake to the right. So Bob has made a new assertion. He's moved his stake to the right. Alice might then make another assertion on top of Bob's, even while her first one is under consideration. And she's therefore required to stake there. So this pipelining process can operate at any time. And in fact, the normal state of an operating chain is like this, that you have a linear pipeline sequence of assertions. Those assertions are all right because nobody wants to lose their stake by asserting something false. They aren't challenged because nobody wants to challenge a true assertion and lose their stake. And so the normal state of things is you have a sort of frontier of assertions that marches along, and behind it you have a frontier of confirmations that marches along behind. By allowing this pipelining, we can always keep the validators busy. We don't have to stop the world while the system waits to figure out whether something has happened. Okay, so we can make progress all the time, even when deadlines are long or even when there are disputes. People can keep building out the truthful branch. Honest validators can always build the true branch. Nothing ever stops them from continuing to build it. Dishonest validators can build out a false branch if they want, but everyone else can ignore it, knowing that that branch will eventually be pruned away. Okay, now you might worry that it's expensive to keep track of all of this on-chain, but there are a bunch of tricks you can use to reduce what needs to be tracked on-chain. In fact, you only need on-chain, on the L1 chain, to track the hash of the latest confirmed state, a single hash that summarizes that state and the entire history that leads up to it. You need to track the hash of every leaf of the tree. If you have the hash of a leaf and you have the hash of the root of the tree, it's easy to prove that any particular node is a node in the tree by doing a set of Merkle proofs. And for each staker, the identity of the stake and the hash of the state it's staked on. Okay, this gives you trustless safety and liveness, and it's going to give you a trustless finality. I'm going to go quickly past this because time is running low. But you get the trustless properties that we talk about, and I'd be happy to explain later out of band why. I want to talk about time messages and interoperability. This is kind of an interesting little problem. The problem here is that it's hard to handle time at L2. Legacy programs like to ask in Solidity block not numbered, that is, what time is it? What's the current block number at L1? At L1, the result of this is determined when the transaction is put on chain and executed. But at L2, the validator needs to propose what happens in the computation of your transaction. And so you can't have something that's determined later. You can't have the outcome of a computation depend on what time it is later when this thing gets adopted on chain. So the correct outcome of an assertion has to be unique. It can't change. The truth value of an assertion can't change over time. Also, L2 execution is asynchronous from the L1 block clock. So how are you going to tell applications a consistent story about what's happening with time when you're in this setting? So in a previous paper, we talked about how to use time as a precondition. The idea is that you label each assertion with lower and upper bounds on the time when that assertion can be accepted, and the assertion is treated as moot, neither true nor false, outside of those bounds. Now the application can ask, what are the current time bounds? And it will be given the time bounds from the current assertion. That operation is deterministic and is always correct. And because the assertion is moot outside those time bounds, it will always be true at the time that the assertion is accepted. So execution is deterministic, and that's great. You give an interval, but real applications just say, what time is it? They want a single scalar time. So what do? What if the app asks for the time? Well, a pretty good solution actually is to take the max over the lower time bounds on all of the assertions you've seen so far and tell that to the application as being the current time. It won't be too far in the past, and it has the good properties of time. It never decreases, and it's always within the current time bounds. I've given a proof sketch in tiny print up here. But the layer 2 runtime actually has to prevent the application from seeing anomalies, because that time might lag a little bit behind the real time, so there might be incoming messages that are time-stamped after that. And you don't want messages to appear to come from the future. So the best solution actually is to take the max of the assertion lower bounds you've seen and any of the message timestamps that have ever been visible to the application level code. Now the interesting thing about this is neither L1 nor L2 can enforce this, this property alone. The L1 doesn't know enough to provide a consistent API to the application, but it can enforce time bounds. The L2 runtime system can see the current time bounds, but also see certain weirdnesses, like messages tagged in the future. But the L2 runtime is written by us, and we know what we're doing. And the L2 runtime is able to show a consistent and sensible notion of time to the application. So this is another example of how the use of an L2 runtime is pretty beneficial. Okay, so some takeaways from this. The branch and prune approach to state management allows high performance and very strong guarantees of progress, of safety, liveness, and finality. There are substantial advantages from compiling everything into a single L2 program per chain and including a substantial runtime component in that. And also there's a surprising amount of what you might call systems problem solving that's needed to make a system like this work. To go from diagrams in a paper to a system that you can compile real code against, you have to solve a bunch of really interesting and difficult systems problems. Okay, let me take just 1 minute for a shameless commercial shilling. Arbitrum Rollup is a commercial product. It works with general smart contracts. Our compiler works with legacy Solidity code. We have plugins for the standard front-end system, so you can port existing applications very cheaply to run at L2 and get those benefits. We have easy tooling for launching a chain for your dApp. This is the first roll-up system for general smart contracts to be actually available and working on testnet. You can go to the obvious place on GitHub for Off-Chain Labs or developer.offchainlabs.com for more information. Also, we're hiring. Thank you. Questions? Got one right in the front.
Oh. Is this on? Could you turn this on?
So
I'll
what?
repeat the question if it's mic doesn't.
So what if Alice proposes a state change to the machine and Bob didn't know about it and proposed a conflicting state?
Right. So what if Alice proposes a state change and Bob also proposes a state change who didn't know about it? So when you propose a state change, that is recorded as an L1. That is recorded by a layer 1 contract. And so either Alice's or Bob's proposal will be accepted as pending by the L1 contract. And if Bob then makes a proposal starting that wants to branch off from the same point, the L1 contract will not accept that. Only Alice's will be the real one. Bob is free to propose another one off of either of those things. But the posting of these contracts, of these proposals, is an L1 action. And therefore, they're deconflicted by the L1 contract. Ben.
Hey, Ed, I really liked what you mentioned before about the sort of safe speed at which this chain can operate based on other validators catching up. Because if you make more assertions than anyone can validate, they can't dispute it. Yeah. How do you think about sort of validators that are like late to the party, so to speak? So what if I'm a validator and the chain's already been running for a year?
Right, so as you say, there's two separate issues. One is a validator who is sort of caught up and will it fall behind? You need to make sure that doesn't happen. But if a chain has been running for like a month, and then some validator just shows up and says, hey guys, what's going on? There are two things they can do. One thing they can do is they can start at the beginning of the chain and work their way forward. And if they can go faster than the chain has gone in the past, they'll eventually catch up. But that might take a long time. The other thing they can do is if they can find some other validator who will give them a checkpoint of a recent state. There's enough information available on chain that they can verify that that checkpoint is correct, and then they can go forward. On a well-run and well-curated chain, let's say a dApp developer wants to run a chain for their dApp, that dApp developer ought to run a service that makes available recent checkpoints so that anyone who wants to validate can go there, get a checkpoint, and they'll be able to make sure that it's correct. You don't have to trust that person, but you do need someone to make that checkpoint data available to you. And it's a best practice to do that, but at the protocol level, we can't force that to happen.
All right, we have time for one more quick question.
So how do you then avoid trace between two validators who have the latest state and trying to submit their proposal at the same time? One of them will lose the transaction and will have to pay gas, and it can happen all the time.
Yes, right. So if two people, and this is related to the earlier question, if two validators try to submit at the same time, really simultaneously, they will, the first one will pay full gas. The second one will pay only a little gas, because one of the first things that can happen when you submit a proposal is that the on-chain component can say, are you proposing to assert from something that is a leaf? So it's just that leaf check that you have to pay for before your transaction will revert. That said, so I'll say that. The other thing I'll say that is in practice, when you run a chain, the dynamic that we see is that one validator will be a bit ahead of the others. And so you'll tend to see the same validator making proposals over and over, and other people not trying. Other people being just a little bit behind that one lead validator. It seems that one rider gets out in front of the peloton a little bit, and the other people are just following. That's a dynamic that has emerged from the protocol, not by design, but just because that seems to be what happens. If this is an issue, you can have someone who is designated as kind of the lead validator who will make proposals, and other people will only step up if that lead validator is not functioning. But that's not a core part of the protocol. That's something that you can arrange out of band if this looks like a problem. Our experience, which admittedly is somewhat limited, is that this doesn't look like it's often a problem in practice. Happy to talk about that more offline.
All right, let's thank the speaker again.
Thank you.
And the final speaker of the session is Asimakis Katis about proof of necessary work and stateless verification.
Where do I put this guy? HDMI. We're good? Cool. Thank you very much. My name's Aki. I'm a graduate student at NYU, and this is joint work with Joseph Bonneau. Today I'm going to be talking about how you can very succinctly verify state in blockchain-like protocols, and more importantly, how you can incentivize that process when it's expensive. So we start at a familiar theme, that when you have a new light client, everybody can hear me? When you have a new light client, or any client that wants to trustlessly connect to the network and joins the network for the first time, they see this. They need to download a lot of bandwidth initially, and then more so every day. And then not only do they need to download this bandwidth, but they then need to do a lot of computation on top of it. And that, unless you have a lot of processing power and memory, that is going to take a long time. And not only that, but in terms of usability of these blockchain based protocols, the more people use them, if you're going to be storing everything, you're going to see a blockchain size that is increasing. And I do think this is a little bit out of date. But the idea is, how can we ensure that we don't really we keep all of the trust assumptions for the miners that are joining or the validators that are joining, but we ensure that they have to use the minimal amount of resources for this. So there's been a bunch of work on this, but the main idea is that there is a fundamental trade-off between the notion of trust, so how much trust are we okay with the validator losing, and efficiency, so how fast can they compute, and as a result, how much memory and how much CPU power do they need. And in general, this is sort of the state of play. A full client is one that doesn't actually need to connect to anybody other than just one other alert node that's going to give them the whole blockchain, and then they can validate it themselves. In the initial setup, so the first time that they do this, when they join the network, they need to download the whole blockchain. It's probably around 300 or so gigabytes right now. And then every single day, they need to download all of the different blocks, and they need to actually validate the blocks and double check that everything is fine. Now, in light clients, where you only give headers, so where they only verify the proof of work, this is much smaller by a couple of orders of magnitude. But obviously, this comes with certain trust assumptions, trust issues, in the sense that, well, you're not validating everything, so there are certain things that you open yourself up to. And finally, an ultralight client would be you just validate latest block, don't really ask too many other questions, and of course, the trust model gets even worse there. So we really want to do better, and we want to figure out what kind of primitives we can use to ensure that we can reach optimal sort of results for this while not compromising on the trust model of these clients. So what has been done in the past here? So in prior work, there's been two real main axes of work here. So the first one is on transaction verification. So if you start at the beginning and you have T transactions in the system, so from Genesis block all the way to your current block, then you're going to need to do something linear in T in the naive way, or at least in the full miner context, and actually sit down and make sure every single transaction is valid. And there have been some optimization in this. So in Mimblewimble, they use a UTXO set that is upper bounded by the total number of transactions, but which can be substantially less. Vault uses a different approach that also involves altering consensus. And the second approach is faster POW verification. So this would be what the light client was doing. Work on that has involved in bringing down the amount of time that this would take to logarithmic in the total number of blocks. And we hope to do better than that here. And we started this moment where, indeed, blockchain verification for all of these different clients is inherently wasteful, in the notion that every single client that joins is going to do the same thing. They're going to download all of the same data, and then they're going to do all the same computation. And that, to me, sounds like a place where we can improve on, where we can do a little bit better, because there's a lot of work being put in on this. And this is exactly what verifiable computation does. So the idea is, the setup is, we have an untrusted prover and an honest verifier. So the idea is, how can the prover prove things to the verifier about an arbitrary statement, an arbitrary predicate, and get some sort of knowledge extraction out of it. So the setup is, you have a program F. In our case, this can be anything. And then the honest verifier wants to know the evaluation of F on X. And it gives X to the prover. And the prover verifies that indeed the statement S, that F of X is equal to some Y, is true, and provides a proof of this statement to the honest verifier. That the verifier will then double check that everything is fine, and if this has been constructed correctly, we'll be able to extract the knowledge that indeed this is correct, the high probability. Now, of course, you also have other verifiers, and if these proofs, pi and x and the input are very small, you could even just send it over to them, and these can be really, really small. So this is really the ideal where we want to go. We want to make sure that you take a client that has 4 megabytes of RAM or whatever, and make sure that in almost instantaneous time they can have as many guarantees of correctness with as few compromises on trust. So how does this affect the blockchain? So take a look at BI here. This is the state I, so the state in our case is a Merkle tree, and a quality QI, because we're working strictly in Nakamoto consensus here. And one way to solve this issue using verifiable computation is you have a big blockchain, you're at block I, and then if you can encode some sort of predicate, that says, BI changed to Genesis, all transactions in the middle are valid, the aggregated work is this, and we're actually at the right state, we should be done, right? And this proof should be able to tell us everything we need to know, that every single transaction here is correct and verify state. Now the problem with that is that this scales with the total number of blocks. So you're always really going to need to feed all the transactions into your proof. Problem with that is that we're back at square one. We're back where we started, at the moment where you have T transactions and you need to do something that is omega T at this point. Well, we want to do better than that. And the solution that has been looked at for this is to build recursion using something called incrementally verifiable computation, which is a specific part of the specific primitives that we're going to use. So the idea is very similar. But instead of actually doing a computation for all of the I proofs, you're going to be only checking the last. So you're really going to be checking the transition from the previous block. And the idea is now, instead, BI doesn't change to B0, it changes to BI minus 1. It only checks the set of transactions in between, so the ones that are transitioning, the state checks. So I also added the commitment because it's going to be important here. So we're also committing to the state S. And ensures the quality is correctly computed. And then the key part is that it actually then just verifies the proof for the previous block. And by induction, that means that all the way down to Genesis, you're going to be able to make proof of knowledge claims on this. Or at least that's the hope. So just another way of seeing this, in a sense, these proofs encode valid state transitions with this added idea that we're also linking back to Genesis. And this is how sort of this would work out. Here you have, the PI is the prover at the ith moment. They take in S I minus 1, so the state previously. They take a set of transactions. They compute it. They compute what the new states should be, give it all to PI along with the previous proof. New proof comes out. And if you give the new state and the new proof then to the verifier, which is at the bottom, the verifier can take state and the proof and then check to see if it holds. And given the context of what I said previously, that would be sufficient to verify the whole state of the system. But because we really want the verifier to be really small, we can use the commitment. So here I called this RT because it's actually a root of a Merkle tree in our implementation. And the idea is that this is really, really small. It's constant sized. And therefore, we're still keeping alive this dream that we want to be verifying these things on smartphones or whatever. So before I talk a little bit about what we built, I just want to talk a little bit about this security assumption here. So we're doing Nakamoto consensus, but we just want to be able to ensure that the things we change in the protocol allow very light clients to be able to verify. However, in order for all of this to work, the verifier should be able to verify, to locate any prover that is current or synchronized or honest. And more specifically, they need to be able to prevent this kind of situation where you're at the top of the chain, the highest quality, and somebody, a forking prover, goes halfway through and tries to do something naughty. You as a verifier, would take in both of these things, and then because the quality is something everybody can see, you ask yourself the question, well, who's bigger? And that's going, so that really ensures. But this is something to keep in mind in Nakamoto-based changes. So we're back to where we started. So what does all of this achieve? So our contribution is that indeed these succinct clients can, in the initial setup, receive about 1 kilobyte of data. So this is based on an instantiation with certain primitives I'm going to talk about in a bit. And yet the trust model in this context, it only really just needs access to one proof of the longest chain. And then they should be fine because they can verify this proof, and because of all of the arguments previously, it should work out. Now, I should just note that this trust model is with respect to the light clients. Now, there may be also some extra assumptions based on how you choose to instantiate your proof systems, which, things like trusted setup, but I'll be talking about that in a little bit. So a few things about the prototype. So we built a prototype of this thing because we wanted to check whether it's feasible. And our prototype, however, is a simplified version of a Bitcoin. It's account-based. It has very simple payment functionality. It's not equivalent to Bitcoin, strictly weaker in the sense that you only have one-to-one payments, no really fancy scripts, no UTXOs, and it uses a reference implementation of libsnark at 80 bits. It has 2 to the 32 accounts, and the predicate size is fixed. So every single time that this thing fills up, you'll need to restart it and reset the ceremony for those that are more familiar with snarks. But the important thing for us was to establish the feasibility of something like this and check how big these proof sizes could be. So the numbers that we got on this, so proofs are really small, and really importantly, regardless of the total number of transactions you're verifying every single time, so at every single block, the proofs are always going to remain around the same size. And this is also the case for the verifier column. So this is really the important thing here, that our verifier always going to need 1 or so kilobytes in memory requirements. This is the verification key for those that work on snark-based systems. And computation time is almost instantaneous. And both of these things are going to be constant regardless of the total number of transactions. On the prover side, these things do scale, so super linearly in the prover's complexity. But that's okay, given that, in a sense, the prover, as we'll see later, is also going to be doing other more computationally intensive stuff. So this is sort of the initial part of how can you do this compression and ensure that these light clients can have trust, can have trustlessness, but still verify something like this. So this really leads to one critical question here, and these are really expensive proofs, and they do something we really like. Namely, they give us all these really great, final results. You can verify the whole chain. You can do really powerful stuff, right? But it takes a very long time. You saw 30 transactions, 100 sections on a lot of cores. That's not really optimal. So really the question then is, who's going to compute these proofs? So Coda Protocol is working on a product that relies on incrementally verifiable computation to solve this very problem. And their approach was, well, we're going to make proof-of-stake validators solve this issue. And this works for them because they use a proof-of-stake system. In this work, we focus on proof-of-work miners. So we want to retain Nakamoto consensus. We want to retain all of the different properties of that. But we want the proofs to be the outputs of this puzzle. And we denote this as proof of necessary work. Namely that if the proofs validate state and also are the output of the proof-of-work puzzle that does satisfy fairness guarantees, which we'll talk about later, we denote it as such. So what's the big deal? Why can't we just do this, right? To go back to where we were, just add an extra thing inside your state transition function that says, also do proof of work. Take your state and take your potential nonce and hash it and see, and do all of that inside your proof. Sounds good, right? The problem with that is that it doesn't satisfy this idea called of progress-free puzzles. Namely, we want to make sure that the puzzle that is running a solver for t times in p parallel cores should find pt times as many solutions. So it should scale with the total number of solutions. And this is really important if you actually want to make Nakamoto consensus work with the security properties that it has. And this is because the incentives really break down otherwise. The important thing to note is, there's going to have large miners and small miners. In the normal case, normal case I'm saying in Bitcoin's case, double SHA, everybody's just churning on nonces. And when they find a nonce, they publish it, everything is fine because this is a Poisson process. However, if at the end, on top of that, you need to also compute a proof, because remember, first you compute the answer in the previous slide, and then you generate the whole proof, you're going to add yourself a big chunk of extra computation that you need to do that doesn't really change too much. So really the only part of this that's progress-free is the part that's finding the nonce at the beginning. And that's really going to disincentivize, or at least make small miners incapable of winning in this game. So this is really a problem that we wanted to deal with. And I just want to give a little bit more intuition about what that actually means. So the amount of time it takes to search for a solution and the amount of time it takes to prove a certain such proof, that ratio really kind of quantifies the problem that I want to sort of highlight here. So initially, assume the case you're asymptotically working in the case where creating a proof takes almost instantaneous amount of time. It's really cheap. Well, finding a nonce is the hard part, which is the more progress-free part. So a very short proving time means that we're moving almost towards progress-freeness. However, as you've seen, very small proofs means very few transactions in the proof. This means that it's got a very slow rate of blockchain updates, and that affects throughput if we're going to be keeping block frequency constant, which we've assumed throughout this. The other side of this is that, well, what if finding the nonce is really easy, and then creating the proof takes a very long time? That solves the throughput issue. But that, however, means that long proving time means that it's not progress-free. Namely that, in the limit, the fastest prover is always going to win. And that's really no good for us, because then we don't get any of the security properties. So the idea that we had here is that we wanted to make proof generation the proof of work puzzle. So the way it would work is that you have a set of transactions. So this is the inputs to find block, the block I-1, and the difficulty. You update the state based on the transactions on the previous state. And then you just do the churning as you would normally. So you generate a random nonce, and then you generate a proof based on this new state and the nonce. And then you check the hash, and if it works out, then you return it. Now, this resolves the initial issue that we had, namely because you need to generate the proof to check difficulty. You can't check difficulty before generating the proof. And that's important because you can't then fall into the issue that you did before. So yeah, so let's keep going. We don't really, oh yeah, and the proof is ready to publish, and it verifies if the prover is honest. But, you know, let's not try to do too much work. Let's try to keep the predicate unaltered, generate pi, and then accept if difficulty holds. So we're adding a nonce, and this nonce is randomly sampled, and this changes the proof, so it changes its hash. And even if we switch out a bit of the nonce, it's going to change it unexpectedly. And you know, the probability of success is exponentially distributed, which is what we wanted. Now, the problem here is that we can change the nonce without really recomputing the whole proof by like saving on certain parts of the proof. And unfortunately, this favors returns to scale. But what do I actually mean by that? So I mean that work is indeed amortized between proofs. So if this green part here denotes computation that needs to be done to generate a proof, then if I just tweak the nonce a little bit to a nonce dash here, it may very well be the case that only this part needs to be recomputed. Similarly for transactions, all right? This is a big problem because you can reuse work. And we're back to where we were before, so that we have similar issues, right? Because if you're creating the proof, it takes a certain amount of time, and then finding tweaks like this means you can be very, very cheap in recomputation. It spoils the progress-free property that we require and also affects fairness. So what really does this all boil down to? It boils down to the fact that we probably need a security goal that we call epsilon amortization resistance. So if we have a certain function f, here that's our prover, it's got access to an oracle, so we're working in, so the oracle in our case, in our architecture, would be modular exponentiation. It's the hard computation. Then, you know, if it takes this oracle n called, this function f n calls to the oracle to evaluate one instance, for L different instances, it should take around L times n. So this is really just a high-level idea of what really is it that it needs to satisfy. So how do we do that in our case? So well, the general approach would be, you know, you take something random that commits the state, so that if you switch out any part of state, then that changes randomly. Because remember, that would completely change in the previous case when we have our tweaks. And then you want to modify the prover circuit in a way that, on the one hand, you're still proving knowledge in the exact same way, that you're actually still proving the same underlying predicate, but the way that you get there involves passing through variables that change unpredictably. Variables that, you know, in our case, will depend on rho. So even if you switch out one bit on your nonce or one bit on your state, rho is completely different, and you won't have any information about what these intermediate variables are, even though the proof of knowledge you're doing is the same. So the challenge is that this needs to be efficiently computable. So the way that we did it is we noticed that in our prototype, we have a massive amount of all the constraints being the evaluation of the of hash functions. And one of the very cheap hash functions to implement in the proving systems that we used is the Pedersen hash. So the idea that we had was generate this row and then try to inject it in all instances of this hash function, so that every single part of that hash function, or the vast majority of the variables in that hash function that do the verification, change unpredictably. And we leverage some specific properties to Pedersen to do so. But the good news is that it's still efficient inside the snarks that we use. Just so overall, this result of masking adds 20% overhead vis-a-vis an unmasked evaluation. So if you're verifying some Pedersen hash, and then you're verifying it with the masking, it's going to take about 20% more time. And then we put this inside, and we end up getting randomizability in a way that allows us to argue for amortization resistance. However, what I'm not saying, there are limits on the efficiency of Nakamoto consensus. More specifically, if we really want perfect efficiency, namely if we want all of our work to be necessary, we need perfect verifiable computation, so we need to generate the proof immediately. But then we also need to make sure that the first moment that you're running a nonce, you're going to immediately get the right answer. So in a sense, what I'm trying to say is that it really just requires one entity to be doing all of this work. So for this reason, we have proposed a different efficiency metric, namely that the necessary work done, because here we do have necessary work for system validations that's actually done, as opposed to currently, and divided by the total work performed. But the important thing here is that actually our proposal maintains the redundancy proportional to the number of miners in Nakamoto consensus. We just allow us to save some. So I'd just like to take the last minute or two to talk a little bit about future directions or something like this. So we are really interested in looking at how much better we can do in proof generation if these are distributed among different participants. So if there is a way to do distributed proof generating using the kind of architectures that we built upon, would this be compatible with a mining pool structure? So you just have some mining operator that can distribute a massive, massive proof, because we can reach order of magnitude changes, and then is this something that can be done? What are the research challenges in doing so? There are certain issues that come up. But the other thing is that because we use things that can encode any predicate, this can efficiently handle smart contracts. Of course, it's going to be bigger, but it still bootstraps in the exact same way. And similarly for privacy or other kinds of applications, as long as you're working in the context of a state transition or a replicated state machine. Then there's the issues of, well, you're using these proof systems, incremental verifiable proof systems. They're very expensive in some ways, and they also have certain properties that are not so great, like some are not quantum resistant, there's trusted setup, and that can affect a lot of what we do. But because our changes were based on this predicate, and more specifically on leveraging properties of a certain function, we believe that it can be adapted to other IVC systems if and when they do come out and are more efficient. We just need to take a look at the assumptions. And then I would just like to end with, if this is something that people are interested in, generating these kinds of things, what kinds of speedups can we get from hardware acceleration? Can you build ASICs or FPGAs that compute snarks really efficiently? And if so, can this lead to better numbers? So yeah, thank you.
Any questions? So does this require, because I was thinking during the talk, is it a problem if you can grind just on the proof? Because right, a lot of snarks like ROT16, if you have one proof for a statement, you can change it without recomputing a proof. So it seems like does it require like having a snark where the proof is deterministic? Like
yeah.
So how do you? So what snark exactly do you use? Like how do you achieve that? Or?
Well, so you're sorry. When you mean unique, you mean that you may be able to get a different witness?
No, I'm saying so. You have the witness. You fix the witness, the nonce. Mm-hmm. You get a proof pi. You hash it. It doesn't satisfy the difficulty.
Yeah.
In saying ROT16, you can just now modify the proof with very little computation to get another proof for the same statement, and so you could maybe grind on the
Well, the idea is that by setting row, which is specific to the nonce, all of the internal variables, all of the field elements inside, the things that you need to exponentiate by, are going to be deterministic functions of this new row. So you're going to have to do multi-exponentiation on unpredictable variables that you then have to take a product of.
Okay.
I don't know if that answers your question.
It doesn't. I'm not sure, but maybe I'll check if. All right. We can offline maybe continue, but.
Hi, we've had to do something very similar, but for a different consensus protocol used Raft. So the process to be able to find the validator node actually performing the transaction finality and arriving at the deterministic nature was going through tons and tons of logs and assessing. So it was an extremely cumbersome process, and what you have shown is for a different protocol altogether. But going forward, for devoid of any consensus protocol chosen, this process has to be inbuilt for blockchain systems to scale and secure, appropriately. So, are you also working on other consensus protocols along with proof of work and proof of stake?
So my work here, and mostly the motivation, was to retain all the properties of Nakamoto consensus and see what we can do to the system that can give us better guarantees. I haven't done any work in other consensus protocols on this. We focused on retaining the proof of work guarantees by trying to ensure that the progress-free properties are retained. But that's very specific to proof of work.
Right, thank you.
All right, let's take other questions offline. So let's thank all the speakers of this session again.
Oh yeah, it's already 10 past.
Yeah. Please take seats. We have 2 talks in this session. The first one is by Florian Tramer. He's going to talk about remote side channel attacks on anonymous transactions in Zcash and Monero. Here is Florian.
Okay, thanks for the introduction. Can everyone hear me? I'm going to take that as a yes. Perfect. So yeah, I'll be talking about remote side channel attacks on anonymous transaction and sort of illustrate how these attacks can apply to Zcash and Monero. Full disclaimer, we disclosed all of this, all the things I'm talking about here to Zcash and Monero, and everything has been fixed. So if you do actually hold money there, or if you care about the privacy of these coins, no need to worry. And this is joint work with Dan Monet, who's my advisor here at Stanford, and Kenny Patterson, who I was visiting at ETH Zurich last summer when we started this work. So just to give a bit of an idea of how these attacks might actually impact users, we're going to talk about a setting where we have a user, let's call her Alice, who's, say, publishing things online as a blogger, as an activist, so things that she might want to say anonymously. She wouldn't necessarily want people to be able to tie this content back to her identity. But at the same time, she might want to be paid for her efforts for writing all these cool blog posts, so she's going to put out a payment address for a cryptocurrency on her website, say a Bitcoin address, so that people can give her donations. And this is, of course, going to be a problem for Alice's privacy if she just uses a sort of a standard non-private or non-anonymous cryptocurrency to do this. And there's essentially 2 bad things that could happen. So every time that Alice is now going to send a transaction into the system, she has to sign this transaction using the key that she put on her website, on her blog. And so anyone who sort of observes the network can just see that a transaction from the activist has been created and sort of tie this back to the machine that actually generated this transaction and sent it out into the network. And the other way around, if someone wants to pay the activist, this is also going to be easy to detect in the network because the transaction is sort of going to say this transaction is for the public key that is on the blog, and so any adversary who observes the network can tell that Bob here is sending money to this blogger. So the solution for this comes from anonymous transactions. So in an anonymous transaction system, at a high level, you can think of transactions being roughly the same as, say, in Bitcoin, except that everything is kind of encrypted. So you would send in a transaction where the amount of funds are encrypted, the identity of the recipient is encrypted, the identity of the sender is encrypted, and you have to add some kind of cryptographic proof to this transaction to sort of make sure that things are actually valid. But from a cryptographic perspective, this transaction leaks nothing about these secrets. So someone who just observes this transaction in the network can't now tell that this is actually a transaction that's being sent by this blogger. And similarly, if someone sends a transaction to this blogger, no one can actually tell that this is a transaction that's meant for Alice. And these are exactly the kind of properties that our attacks actually break and circumvent. So there's sort of 2 ways you can think of the attacks that I'm going to present. In one case, you can think of the attacker here, knowing the blogger's public key because they can find it on her blog, and just sending a transaction to this address into the network. And then we can actually show that there's things the attacker can do to sort of figure out which machine in the network, which peer-to-peer node actually belongs to the activist. And so this could then be used to, say, re-identify, de-anonymize the activist or geolocate her, and so on. And similarly, when a different user, an honest user, Bob, sends an anonymous transaction to Alice, we also show that an adversary that sort of actively participates in the network can sort of learn that this particular transaction is actually meant for the activist. And we'll even talk a little bit about how an adversary might be able to determine how much money is being spent in such a transaction. So more generally, the results we have in our work are remote side channel attacks that sort of exploit leakage that comes from various components of an anonymous transaction system. So these aren't attacks on the sort of high-level protocols that these systems implement, but really on the implementation of different components of the system. And what we show specifically in Zcash and Monero is that these attacks let an adversary determine which node in the peer-to-peer network belongs to the payee of any transaction in the network. And as I've said before, this can let an attacker determine a user's IP address given their public key, or it can also be used to link diversified addresses of a user. So this is a property of systems like Zcash and Monero that sort of allows users to create multiple public keys that are sort of aliases of each other, but that shouldn't be able to be linked to the same user. And our attacks can break this unlinkability property. In the case of Zcash, we also show a few other consequences of these attacks. So sort of a weird one was that one of the vulnerabilities we found actually lets an attacker remotely crash Alice's node in a way that can't actually be easily recovered. So whenever she'll try to relaunch her node, it will just crash again. And we also show side channel attacks on cryptographic components. So there's a way in which an attacker could try to launch a timing side channel that could extract Alice's secret viewing key. And if this key is extracted, you basically break the privacy of all transactions that are sent to Alice over time. And we'll also talk a little bit about how we might be able to exploit timing leakage in the generation of so-called zero-knowledge snarks to learn transaction amounts. And so as I've mentioned, we have disclosed all these vulnerabilities to the affected project, so Zcash and Monero, and they've all been fixed. And, but the general issues we describe here and the sort of lessons we've learned from these kind of issues, they extend to anonymous payment systems in general. And so I think it's quite likely that other systems out there that try to implement anonymous transactions might suffer from similar vulnerabilities or similar design issues. And so if you are trying to or implementing such a system, it might be worth thinking about some of these side channel attacks. So in this talk, I'll focus on two main types of attacks. So first, I'll describe how we can use different forms of side channel leakage to determine which node in the network is being paid by any transaction. And then later, I'll describe some of our work on side channel attacks for snarks. And the rest of these results, if you're interested, you can find in our paper that we wrote on this that I'll link at the end of the presentation. So let's start with de-anonymizing attacks on Zcash. So to understand what's going on, we'll just have to dive a little bit into how receipt of a transaction actually works in Zcash. So again, when someone sends a transaction in Zcash, they send this into a peer-to-peer network, and everyone who participates in the peer-to-peer network will sort of receive this transaction and check whether they're the intended recipient. And so for the purposes of this attack, we just need to think of a transaction as containing two values. There's a bunch of others. One is a UTXO, which in Zcash is essentially a cryptographic commitment to a coin that can later be spent. And then there's also a ciphertext in this transaction, which is essentially encrypted for the public key of the intended payee. And so what Alice has to do when she receives such a transaction is to first try to decrypt this ciphertext using her secret key. And if this fails, well, she knows the transaction is not for her, so she just ignores it. But if this succeeds, well, the transaction is for her. So what she then does is she takes this decrypted ciphertext, which is called a note, and this note should contain the amount for the transaction as well as some randomness. And she then has to check that this UTXO, this committed coin, is actually a valid commitment. So she has to check that this that sort of committing to her public key, to the value, and to this randomness gives back this UTXO. And this is essentially a check that guarantees to Alice that she will later be able to spend this coin, that she received this money, and that it's sort of a valid coin that can later be spent in the system. And sort of the core issue here is that this check takes time. This is a public key cryptographic operation, so it will take a bit of work to compute. And importantly, this work is only done by the user who actually received the transaction, received the payment, and managed to decrypt the ciphertext. So this leads to the following relatively simple attack. It's quite easy to mount, which we call ping. So here what happens is some user, Bob, sends a transaction into the network. The adversary doesn't know who this transaction is for, but he suspects it might be for Alice. So what the adversary is going to do is he's going to forward this transaction to Alice's node, and right after send her a ping message, which is sort of a standard message in Zcash's peer-to-peer system. What Alice's node is going to do at this point is it's going to give this transaction over to its wallet component, which holds all of Alice's keys. And the wallet is going to do this decryption, figure out that this transaction is for Alice, and check this commitment. And once this is all done, the node will finally be able to respond to this ping that was sort of waiting. And of course, the adversary can now just time how long it took for this response to come in and sort of determine how much work Alice's node has been performing, and from there sort of learn whether this transaction was paying Alice or not. And so we actually implemented this attack and validated it in a test network over a WAN. So we actually had the attacker here was on a machine in London, and the victim, Alice, was running a node in Zurich. And we did this experiment where we send transactions to Alice followed by a ping, and some of these transactions are payments for Alice, some of them are not. And the response time in the ping actually clearly leaks which transactions are the ones that pay Alice and which ones are not. And the difference in timing of about 1.5 milliseconds is definitely large enough to be observed even over a wide area network. So what's basically the issue here? How do we fix these kind of attacks? So the problem in the original Zcash implementation is essentially that the peer-to-peer and wallet functionalities, they really correspond to different layers of the protocol, and yet they're sort of intertwined into one single process that Alice runs on her machine. So the Zcash client just runs one process that sort of sequentially receives transactions from the peer-to-peer layer and then sends them to the wallet for processing. And this isn't really the right kind of design if we care about this type of anonymity. What we'd really want is the peer-to-peer node to just sort of act as a database that just receives transactions over time, and the wallet would just sort of pull from this database whenever it wants. And this is the kind of new design that Zcash has now been implementing. And this improved design is actually something that the Monero client was already implemented this way. So the way you can think of this is that, again, you have a peer-to-peer node that just receives transactions over time and just stores these in a database. And then periodically, the wallet will just sort of wake up, ask for all the new transactions, receive these from the peer-to-peer node, and do a bunch of cryptographic processing to figure out which transactions actually pay the user. So you might wonder then, well, if Monero uses this kind of better design, so why is it still vulnerable to some of these side channel attacks? So to understand this, we have to take a deeper look at how this communication between a peer-to-peer node and the wallet look like in Monero. So this is sort of a simplified view, but what happens is that at some point in time, Alice's wallet will request new transactions from the node and say there's a new transaction that has arrived, which is actually one that pays Alice, so the node will send this to the wallet. The wallet is then going to process this transaction, go to sleep for a fixed amount of time, And when it wakes up, it's going to request transactions again, say there's now a new transaction, one that doesn't pay Alice, and this process sort of continues. And there's two sort of sources of leakage here. One is kind of obvious from this picture. I mean, I drew it to make it obvious, is that basically the time between the wallet's requests to the peer-to-peer node leak whether Alice was paid by the previous transaction that it processed. Because when it processes a payment for Alice, again, it has to do more cryptographic work to ensure the transaction is spendable. And so this is going to delay the time until it can make its next request. And another source of leakage, which you can't really see here, but is actually something we found, also a sort of a design flaw in Monero, is that there are situations where the wallet will only make a request if it recently got paid. So in some cases, even the fact that a transaction request was sent from a wallet to a node leaks whether the wallet was recently paid. And so, of course, this means that if the adversary can observe the communication between a peer-to-peer node and the wallet, all of these things leak to the adversary. And this will be the case if you say have a mobile wallet that connects to a remote node, which is something that happens actually quite a lot in Monero. A lot of users set up their wallets this way to sort of talk to a remote node over the network. But even worse, we found that this communication between wallet and node could sort of be inferred by a remote attacker even when Alice's node and wallet are sort of collocated on the same machine. So in this case, the adversary is remote. He can't really observe what's happening on Alice's machine between the wallet and node. But so here we found another sort of design issue that caused leakage to a remote adversary, which is due to sort of suboptimal handling of concurrency in the Monero node. So what happens here is that when the wallet requests transactions from its peer-to-peer node, what the node is going to do is it's going to take a global lock on its entire database because it sort of wants to make sure it doesn't have multiple threads sort of interacting with the database simultaneously. And so now if the adversary who's sitting on some machine somewhere remotely at the same time makes a request to Alice's peer-to-peer node, say to look for a transaction that it can't find, this request is going to be blocked because the lock is being held over the database. It turns out that this lock is actually being held for quite a long time because the node will retrieve the transactions that the wallet is asking for, validate them, and only then release the node and release the lock and send back the transaction to Alice's wallet. And at that point, when the lock has been released, it can also respond to the adversary. And so again, here, the fact that a request from Alice's wallet was in place is actually going to delay the responses to the adversary quite significantly. And we show, again, in a test network over a wide area network that the adversary can actually very reliably infer at what points in time Alice's wallet is requesting transactions, and this can be then used to leak whether Alice's wallet has been receiving payments recently. So how do we really fix these issues then? So again, the main point, the main thing we should strive for is to have the peer-to-peer node and wallet functionalities of a client be fully decoupled. And so what that means is what we really want is that sort of independently of anything that the peer-to-peer node does, the wallet should just at fixed intervals ask for all the new transactions and blocks and then process them locally. And the sort of important thing here, which wasn't handled correctly originally in Monero, is that what you really shouldn't do is have the wallet sort of sleep for fixed amount of time between requests, because this leaks how much time you've actually taken to process the responses to those requests. One solution you might think of is, well, we're just going to randomize the amount of time we're going to sleep, and this is actually something that was originally proposed as a fix for these kind of attacks. But this doesn't really work in general, because an adversary can sometimes just replay these attacks multiple times to just sort of average out the randomness. And so a much better approach here is to essentially ensure that the wallet always issues requests at a fixed time. So say at the beginning of every minute, it issues a request to the node, receives new transactions and blocks, validates them, and then sleeps until the start of the next minute. And so in this case, nothing that the peer-to-peer node sees essentially tells it anything about how much processing time, say, the wallet has been doing, and at that point, this also can't leak to a remote adversary. And more generally, one piece of advice I think I would have for these kind of clients is that I think it would be a good idea to just use some mature state-of-the-art in-memory database to handle things that the peer-to-peer node has to maintain in memory. So things like UTXOs and part of the blockchain. And in most clients we looked at, it turns out that people had just sort of developers had sort of implemented their own version of a database, sometimes with very coarse locking strategies and so on. And this seems like a source for inefficiency and also potentially attacks. And so these vulnerabilities have all also been fixed in Monero. Okay, great. So with the 5 minutes I have left, I'll talk about something slightly different we looked at as part of this project, which are timing side channels in zero-knowledge proofs. So recall that when a user sends an anonymous transaction, all the secrets in the transaction are sort of encrypted so that no one can see them. And then we have to add cryptographic proof that essentially ensures to everyone in the network that this transaction is really valid, that these are coins that Alice is allowed to spend, and so on. And the cryptographic property we want from this proof is what's called zero knowledge. So just seeing this proof should leak nothing about the transaction secrets, so about the keys of the receiver or sender or the amount of funds that are being spent. And so what we were interested in looking at is whether the time taken to generate a proof could actually leak something about these secrets, which is sort of a property that the traditional cryptographic zero knowledge property doesn't say anything about. And surprisingly, we found that in Zcash's implementation of ZK snarks, this was actually the case. So what the prover does in Zcash when generating a proof is roughly a computation of this form, sort of a big sum of basically multiplications of scalars with elliptic curve points, where these scalars, AI, are essentially, you can think of them as a bit decomposition of all the secrets that go into the transaction. So the different public keys, the transaction amounts, and so on. And the crucial optimization that's used in the implementation in Zcash is that if some of these scalars are 0, you just don't do any computation because you know you're just going to be adding an elliptic curve point that's 0 anyways. And so that means that now the time it's going to take you to generate a proof is going to depend on how many non-zero values, how many non-zero bits there are in your secret. And so it turns out that this really impacts how much time the proof is going to take depending on how much currency you spend. So we plot here the time taken to generate a proof depending on how much currency is being spent in a Zcash transaction. And there's actually a fairly noticeable correlation. And it's not necessarily clear how easy it is for a remote adversary to exploit this, and that it might be hard to remotely sort of measure how long it took someone to generate a transaction. But we think there's some situations where this might be possible. Say if Alice makes payments at recurring intervals, or if she outsources proofs to a remote service. So generally, we just think it should be good practice to try to strive for constant time implementations of these cryptographic primitives, like we do for any other type of cryptographic primitives, signatures, encryptions, and so on. So to conclude, I think the big lesson here, which probably most people who have worked on anonymity systems would say is, well, we know this, is that anonymity is really, really hard. And that basically to get good anonymity, you don't only need very strong and provably secure cryptography, you also need really strong system design. In that the flaws that we found here in these attacks, they're most of them aren't really, they're sort of completely orthogonal to the sometimes complicated cryptography that these systems implement. And they really come from sort of design decisions in the system design of these currencies. And one thing we also notice here is sort of something, a lesson we've also learned kind of the hard way over the years when working on anonymous systems, is that starting from a design that doesn't care about anonymity or privacy, and then trying to add anonymity and privacy on top of it, which is kind of what happened with Zcash, which is sort of built on top of the original Bitcoin client, is always a bit of a bad idea, in that then you're sort of trying to plug holes in a sinking ship, and there's always going to be sources of leakage that the original design didn't account for. And well, so it's, in that sense, it's actually very nice to know that Zcash is working on a completely new implementation of their client, sort of from the grounds up, with a much more careful thought being put into the design. So if you're interested in learning more, we have our paper and some extra information on this website. And yeah, I'm happy to answer any questions you might have. Thank you.
Questions for the speaker?
The timing data you presented here, so you measure it from a certain node, right? So, but in reality, each node could be running on different machine, different network environments. So practically, it's almost impossible for you to figure out what will be the right timing to measure, right timing to attack on each node, right? Unless you really get into the node to collect the data already, like you measure like the cryptography encryption gonna take, right? So how practical you think this attack? As in theory, definitely this could be an attack. How practical you think that could be?
Yes, a very good question. So this is actually something that we can, that our attack can take into account. So the nice thing here is that, say I'm targeting some node that belongs to Alice. I don't necessarily know what kind of machine she's running or how fast it is. So what I can do is I can first run the attack a bunch of times with transactions that I know for sure are not for Alice. Say I send transactions to Alice that are payments to myself. And then I can measure how much time it takes Alice to respond to a ping. And this basically gives me a baseline for how fast Alice's machine is for transactions that don't pay Alice. And then later, when a new transaction comes in, I can do the measurement again, and if it's significantly higher than this baseline, I now know that this is actually a payment to Alice. So I can sort of do this attack on a node-by-node basis by just looking at a relative difference compared to a baseline.
Thanks for the talk. Could you comment on the difficulty and perhaps also the performance impact of making these more advanced crypto tools constant time?
That's a very good question. So in general, there is a performance overhead, right? In that if you say, take a look at this kind of operation, well, of course, if you're going to get rid of this optimization, you're going to end up doing more work, and essentially you end up doing the worst case amount of work every time. I would say that's sort of my intuition. I must say I've never really worked specifically on trying to make these implementations constant time, but I would presume that the overhead you'd get would be some small constant, maybe between I don't know, 2 and 4x overhead with a good implementation. And so I think it's worth the effort.
Thanks for the great talk. I wanted to ask whether you have any thoughts about how hard it is to amplify these side channels. So for example, whether you can send like minor variations of the same transactions 500 times without actually having to include it in the blockchain 500 times, making it much cheaper to kind of flood the node with computational overload potentially, things like that.
Yeah, it's a very good question. So let me get back to the picture of sort of two different types of attack we look at. There we go. So basically, in the setting at the top, where the attacker sort of knows someone's public key and just tries to figure out who they are, what's really nice is they can just repeat this attack as many times as they want and sort of get very, very reliable timing measurements. And they can also just send transactions for 0 value. Maybe in some cases, you can even sort of overwrite transactions many, many times to not have to pay fees. And so in this setting, it's actually, you can very reliably repeat this attack to get a very, very confident measurement. In the bottom scenario, where the transaction comes from an honest user, here it's harder because Alice will basically validate this transaction once. And once it's validated it will sort of ignore further messages that send the same transaction. One thing you can do is you can actually run the attack twice. Once when the transaction is first sent into the network, and the second time when it's included in a block. So basically all these timing side channels also exist when a block is being validated, because then the node is going to revalidate every transaction, and again have a timing difference for transactions that pay the user. So in this setting, you can do the attack twice and sort of halve the variance in the noise you might get from the network.
Sorry, we're out of time for questions. Let's thank the speaker again for a great talk. Our next speaker is Daniel Perez, and he's going to talk about broken meter.
Okay, so hello everyone. My name is Daniel Perez. I'm currently a PhD student at Imperial College London. And I've been working on this paper with my supervisor, Benjamin Lifshitz. The paper is called A Broken Meter, Attacking Resource Metering in EVM. And it mainly talks about gas and how we can attack this on Ethereum. And so this paper will also be presented next week at NDSS. So yeah, I'll get started. So first, a quick background. I think here, like most people, should already be mostly familiar with smart contracts and all these things. But I will go through this quickly so we're all on the same page to continue to the core of the paper. This is a short diagram mostly of like a life cycle of a smart contract, which is basically a small program running on the blockchain. So for Ethereum, these contracts are usually written in a high-level language called Solidity. Out of this, you get some bytecode, which are basically a sequence of instructions. On Ethereum, it's a stack-based virtual machine, which is in charge of executing these instructions. Once we compile this into this bytecode, this will be deployed on the Ethereum blockchain through a transaction. When this contract is deployed, it will get its own address. Once this contract has an address, users can then send a transaction to this contract. This contract will run, execute. It can call other contracts and Ethereum, do pretty much anything. And yeah, that's pretty much how these smart contracts are run on Ethereum, at least. And there's one important thing here is that this will be run on every single node on the network. So we cannot just run programs forever or have infinite loops or these kind of things, because it would completely open many attacks on this network. So Ethereum has this concept of gas, which is a way to compute more or less how computationally intensive a program is. So the way this works is each instruction uses a certain amount of gas, which is a unit which is fixed. It was written in the yellow papers and changed a couple of times through hard forks. And it can be either just a fixed value, or it can be dependent on the arguments that the instruction takes. And when we want to compute the cost of a whole program, so the whole smart contracts to run, there is a base cost, and then there is a sum of the cost of each instruction in this program. So something important here is that each transaction has a gas budget, and as soon as this gas budget is reached and the smart contract goes over it, it will stop with an out-of-gas exception, and that prevents what I just said about infinite loops and these kind of issues. And the transaction sender also need to pay a fee for executing his contract on the network, in this transaction. And so this cost is basically this gas cost, which is multiplied by a gas price, which is how much is the sender ready to pay for a single unit of this gas. And this multiplication is a transaction fee. So the more computationally intensive a program will be, the higher the cost of the transaction will be. So here are a couple of sample gas costs. So for like arithmetic instructions or very computationally light instructions, let's say, it's fairly low, so 3, 5. And an important thing here is that as soon as we touch I/O, so as we have to look at the state, to touch the disk, it becomes fairly expensive. So for example, this Xcode size, which is used to see how big the code of a contract is, this requires to actually access storage usually. And as it's much slower to access storage than just to perform a multiplication, it's also much more expensive, so 700 here. And usually the most expensive thing is to actually store something on the blockchain, because this is replicated on every single node, and it's a very expensive thing to do. So it's 20,000, which is orders of magnitude more than for all these arithmetic and this type of operations. So up to here, all good, but obviously it's very, very hard to get this pricing right. And well, if this pricing is not right, it usually means that it's possible to perform denial of service attacks, so to create contracts which are very, very slow, but are not particularly expensive to execute. And this already happened a couple of times in the past. So I think both of these attacks are from 2016, if I remember correctly. Once was exploiting the instruction I just talked about before, Xcode size, which needs to access storage, and so which is very I/O intensive and is fairly slow to execute. And at this time, the gas cost was only 20 compared to 700 now, so it was very, very cheap. And an attacker could basically just like spam this Xcode size, and he could generate very, very slow contracts for a very low cost. So to fix this, they simply increase the cost to 700, which is much closer to how actually computationally intensive this operation is. And there was also an attack a bit in the same spirit a bit after this one, if I remember, which was on the instruction called suicide. I think now it changed name to self-destruct, which is an instruction whose purpose is to basically kind of remove a smart contract from the blockchain, so it resets its code, and all the money that was on this contract, so all the Ethereum, is sent to whatever address is specified to this instruction. And at the time of the attack, it was free to execute because to incentivize people to free the storage used by their contract if they're not using it anymore. And also, if they would send this money to a non-existing address, this address would be created for free. So given these two things, basically, it was very, very cheap for an attacker to just create and destruct contracts. And also because of some implementation issue in Guess, I think, I don't remember the exact details, but it made this very, very slow. And there has been some peak in block creation times in the network at the time. And after this, so this pricing has been revisited. Suicide, so self-destruct now changed to 5,000 gas instead of 0, and the contract creation cost was also increased to reflect the actual cost of the normal operation, of the create operation. So this is mostly for the past attacks. I think there had been a couple more, but I think these were the most important one on this gas mechanism. And so in this paper, what we wanted to see first is, well, is this perfectly fixed, or are there still like potential attack vectors? Or, well, basically, can we still find some contracts which are very, very slow and still fairly cheap to execute? So the first thing we did is to try to analyze right now on the transactions on Ethereum, well, the price and the gas cost and the correlation between the gas and different resources, and analyze all this and try to get some insights out of this. So what we did for this is first we forked the C++ client of Ethereum, and we instrumented this to measure the CPU, so the execution time, the clock time. So we record basically each instruction, we see how long it took to execute, and to avoid a bit noise, we aggregate this over 1,000 every time. We also instrumented memories to see basically when we execute a contract, how much memory is allocated, how much memory is freed, how does this correlate more or less with the gas cost. And well, using this instrumented version of our Ethereum client, we replayed months of transactions and then analyzed so different metrics. So first we started by looking at fairly simple cases. So we started by simply looking at arithmetic instructions, which we thought would be fairly predictable. What we saw straight away is that even for something as hopefully predictable as arithmetic instructions like adding, multiplying, dividing, or exponentiating, it's overall very inconsistent. So for example, multiplication and division, which both have the same cost in terms of gas, have an order of 5 times difference in terms of speed, so it's 5 times faster to multiply than to divide. And even worse for exponential, which is not a fixed cost, but on average I think it's about 10 times more expensive than a division, and it's still almost twice faster. So it means that there's for this arithmetic instructions themselves order of 10 of magnitude in terms of throughput, where we define throughput in this gas per second or gas per microsecond here. So this by itself, it's not a big problem, but it still shows that it's quite hard to get this pricing right. So next thing we wanted to do is to see how this gas cost correlates with different metrics. So the CPU, so the clock time, how much memory is allocated, deallocated, and how much storage, where storage here means in terms of Ethereum. So in Ethereum storage, so how much Ethereum words are allocated or are accessed during the transactions. So given the pricing I showed before, well, we were indeed expecting that it will be mostly correlated with storage, because this is what is the most expensive thing operation in terms of gas. But we were also hoping that if we added more, so if we added memory, if we added CPU to these correlations, it would get more and more correlated, so that basically all of the different resources that a node would use are kind of included in this pricing. And what we saw is that when we add allocated, deallocated memory, so which would sometimes correspond to like some log operations or some, well, anything that the Ethereum node needs to keep temporarily in memory, while executing the transaction, this correlation increases quite a bit. So we have this EIP 150, which changed the pricing of these things quite a bit, which is why we have both here. But after we see that there's a fairly good increase in terms of correlation once including memory. But the main issue here was with CPU. So the time, which is decreasing the correlation, so which means that basically it doesn't seem to be really, at least using this kind of analysis, reflected at all in this gas pricing. So when looking at why this could happen, we figured that like it's mostly due to high variance instructions in terms of execution speed. So some instruction which would sometimes be very fast, sometimes be very slow to execute. And when we looked at this, we saw that well, it was pretty much what we expected. Operations touching to I/O and which need to read the state or often have a very high variance. So for example, for this Xcode size, here's the standard deviation is higher than the mean in terms of execution time. So, well, the next thing here that we wanted to look at is, given this high variance, where we were suspecting that the main reason for this variance is the caching. So we thought that, well, when it's in cache, it's probably very fast. When it's not in cache, it's probably very slow, which would make sense, but which is not reflected in this kind of pricing. And when looking at this effect of cache, so we saw that we focus here on the OS page cache, which is used quite a lot by the backend storage for the Ethereum clients. And well, we saw that on average there is, so we tried to generate random programs and to execute them with and then without the page cache or the cache being filled. And we saw that there's about 28 times faster with cache, so which is fairly important, especially given that the price will not change at all. So to summarize a bit, though, everything that we all the insights we got from these different analyses, so we saw there are like many inconsistencies, and a lot of instructions has high variance in terms of execution time, mostly due to the cache. And well, that overall is very difficult to model this kind of I/O operation and the inherent complexity of all this with such a pricing. So given all this, we thought, well, maybe it's possible to kind of attack this and to find some contracts where we can create a lot of cache misses and these kind of things. But obviously, we didn't want to like do this very naively. We want to try to do this in a fairly systematic way. And so, well, if we kind of rephrase this problem, what we are trying to do is to find programs which minimize the throughput in terms of gas per second. So this is mostly a search problem, or it can at least be fairly simply formulated as one. So here we have a search space, which is a set of all the valid possible programs on Ethereum, which is pretty much an infinite search space. We have a function to optimize, or metric to optimize. Here is the throughput. And our constraint, which is a gas budget. So we don't want programs to be too big because it needs to be able to be included in a transaction and included in a block. So these are more or less the different things we need to take care of for our search problem. And obviously, like this search space is very big, and we cannot like look at everything in this search space. So we used a genetic algorithm to try to approximate a solution or to find very slow contracts. So here I'm not going to go too much into details on the genetic algorithm, and like all the details are in the paper for people interested. But generally speaking, so there were a few things we cared about, which was first to only generate valid programs so that we don't increase the search space even more than it already is. So here, a valid program, there are a couple of conditions which need to be fulfilled. For example, for each instruction, there need to be enough elements on the stack to be able to execute it. The Ethereum stack is, I think, 1024, so we can't go over this. We can't have too many elements on the stack, and we can't also access completely random memory locations because this costs a lot of gas. So these are like a couple of constraints we had when generating this program, so we took care that every single program generated fulfills all these conditions. And as it's a genetic algorithm, we need some mutation and crossover operators. So we also designed these so that two valid programs will always result in a new valid program. And finally, here's something where we kind of took a shortcut because it was not very relevant to what we were looking at, was for loops, we just decided to not include loops, so not include any jump or a conditional jump, as it would not really make any difference anyway in terms of throughput, and it makes the program generation logic much simpler. So then another quite important point here is initial program construction and the initialization values. Well, given we have a very, very large search space, if we want this to converge in a fairly reasonable amount of time, we need to start with a fairly slow program already and improve on this rather than starting with something completely random. So good thing here is that we already have plenty of data from our previous measurements, so that's what we reused. Using these measurements, we basically got the average throughput of each instruction, so the gas per second that it was using. And here the idea was simply that when sampling, so randomly taking an instruction to include it in the initial program, we would assign a higher probability to instructions which were already fairly slow, while we would assign a much lower probability to instructions which were quite fast. So we don't like completely ignore the instructions which were fast, but we still try to get an initial program which is relatively slow and start with something a bit easier to optimize for our algorithm. So I'm now going to talk a bit about the results that we got using this. So with the first program creation, we started, so during the first generation, so the first program created without starting the actual optimization process, we already got an average of around 3 million gas per second. So to give an idea, the average on the exact same machine we were using was 20 million gas per second when we were replaying the transaction. So we already have a 6 to 7 times slower initial program. which, well, tells us that our initialization strategy seems pretty much acceptable at least. And then we can see on the graph here that it continues to decrease fairly quickly until maybe generation 50 to 100. And here we reach already 500,000 gas per second. And finally, at around generation 200 here, we start plateauing at 100,000 gas per second. And so to see how bad this is, it's basically 200 times slower than the average contract, which would be running which was running on the exact same machine. So this is a really, really high number. But up to here, so we have been running everything here on our Ethereum, on our forked C++ Ethereum client. So the next thing we wanted to look at is, so how does this behave on other clients? Is this still very slow, or is it like just a problem inherent to the C++ client? And well, in our results, we saw that basically at the time of doing this, all the clients were pretty much vulnerable. So the fastest client of the three we tested, we tested Alice, Parity, and Guess. Parity and Guess being the two most utilized client for Ethereum. And on Parity, it took around 47.1 seconds to execute 10 million gas worth of this kind of malicious transaction. So 10 million is because this is maximum amount of gas in one block. And so it was 47 seconds for Parity and 75 seconds for Guess. So given that on Ethereum, a block is produced more or less every 13 seconds, this is way too slow. Even on much more powerful computers. So for the first three, I forgot to mention this, for the first three, we tested this on Google Cloud with a fairly normal setup. We had, I think, 8 gigas of RAM with 4 cores or 8 cores, I'm not sure, CPU and an SSD locally attached. And we tried to execute this on Parity, which was the fastest of the three, on a much more powerful bare metal server. With, I think, 32 gigs of RAMs and a more powerful CPU and a much faster SSD. And even though there, it took around 18 seconds, which is still too slow for this node to be able to keep up with the network if an attack were to be performed. And I'll talk about the disclosure process a bit later, but we talked with Ethereum Foundation, with the Guess developers, and and right now the current version on mainnet, which has been fixed and patched, is much, much faster, and now it takes only 3 seconds or so to execute the exact same contract. So in the current state of the main network now, this is mostly fixed for Guess. And so I'll quickly talk about like the basic potential of such contracts, or at least of these contracts, to perform this kind of denial of service attacks. So clearly, like as it's way too slow, a lot of nodes would not be able to synchronize anymore with the network. And well, this usually results in a decreased throughput and a longer time for block production. And as for the attackers, there are a couple which we could think of, but therefore, miners, we have seen a lot of like selfish mining behaviors, and this could also be used for this kind of behaviors if they can prevent other miners to start mining at the same time, so delay them in their mining process. It can be financially viable for them, and there are also obviously like parties hostile to Ethereum who could try to actually attack the blockchain, so attack the Ethereum blockchain. And an important thing here is that it's very, very cheap to perform. So at the time of writing the paper, it would have cost $0.7 to keep some community hardware out of sync for 1 block. So it's less than $1 per block to keep a good part of the network out of sync. Obviously, as a limitation, we don't really know which node is running what hardware. It's impossible to measure, so we don't know how many nodes will be affected. But we still think that given how slow this transaction can get, it would be fairly bad for the network overall. So we disclosed this to the Ethereum Foundation last year around October. We then talked to them and tried to improve a bit on the state. And I have to thank Matthias Egli and Uber Ritzoff from PwC Switzerland, who helped a lot with all these measurements for the disclosure and to write the report. And so during these 2 months, I worked with them to try to see what was slow and how we could improve this. And the Ethereum Foundation confirmed our reward in November and announced this at the beginning of this year. So to finish with, I'll talk very quickly about some short-term and long-term fixes which are ongoing. So for the short-term one, it's mostly twofold. So one which is, the main goal being to improve the throughput of I/O operations. So for these are two variables, the cost of the operation and the speed of the operation. There's one thing is to increase the cost, which has been done already in a few proposals before, and simply making so this I/O operation more expensive. And the other one is to make them faster, so basically reduce the number of disk access that they need to perform, usually by using smart data structures and these kind of things to reduce the execution time. So this is more like this kind of short-term solution. And in the longer term, there are a lot of research avenues going on. And for this, it's there are stateless clients, which are the focus of research right now. I'm not particularly familiar with them, but the very high-level idea is that the nodes don't keep actually track of the state directly, but they receive with the transaction the necessary data and a proof of the validity of this data, so they can execute the transaction only using this. And there's also sharding, which is not a direct solution, but which would maybe decrease a bit the amount of data and state that each node has to keep track of, and which would obviously improve this I/O operation. So yes, this is pretty much it for my talk today, and I'm happy to receive questions. Thank you.
Very interesting talk. Did you run the genetic algorithm on the other nodes as well, or especially the fixed version of, I guess, parity, to see whether now there's other, basically other very expensive things? And then the other question was that, so you said it was like 3 million gas per second for the initialization. What is the most, like if you just copy the most expensive opcode, where does that get you?
So for the first questions, that's something that we actually want to do. We haven't tried it yet, and also because the current genetic algorithm is quite like tightly integrated with the C++ client, but we definitely want to try this. And I think it would be good to try to run this a bit more permanently to try to find these kind of edge cases. But unfortunately, we didn't have time to do this yet. And for the second part of the question, yes, actually, when we look at the result of the genetic algorithm, it comes up with pretty much always the same kind of instructions with the same pattern. So usually it's trying to access non-existing contracts and either their balance, their code size, and this kind of thing. So if we just take like really these parts, we can pretty much get probably even slower. We can get even slower than the genetic algorithm itself because it's not perfect. So a bit more of manual analysis later actually does help.
Any other?
Is also any like a comparison of different low-level key value stores like LevelDB or RockSpeed that may impact the different results of these, for example, I/O-intensive operations?
Sorry, a comparison of what? Sorry.
I mean, using different low-level key value stores, like for example, gas using LevelDB and
sure.
And how that will impact the results.
So for the key value store, I have used the default one, which for this, I think all of them are using LevelDB, if I remember correctly. But I'm not sure how this could influence. I am pretty sure that depending on the caching strategy of the underlying backend, it could change the result quite a lot. But I didn't try, and I am not aware of other backend implementation for either guess or parity, but there might be. I would have to check.
Anyone else? One more question, probably the last one.
Thanks. There's a literature showing that naive optimization algorithms like stochastic hill climbing often outperform genetic algorithms for a fairly broad range of objective functions. Did you try things like stochastic hill climbing?
No, to be honest. So, well, the reason we went with genetic algorithm is that it's quite easy to do this crossover and mutation for bytecodes and for this kind of very simple program. So we went with this, and it worked well enough for our needs. So we did not try to use other optimization techniques here.
Cool. Let's thank the speaker again for a great talk. Time for lunch.
all yours.
Awesome, thank you, Dan. Sweet, so my name is Ben Moore, and I'm the tech lead at Calibra, which is a part of Facebook. And we're contributing to Libra, which is a new digital payments network built on top of blockchain technology and being launched by the new Libra Association. And we're also building a new wallet for the system, Calibra, which we are launching. A bit about myself before we get started. I've been at Facebook for about 10 years now. Before Facebook was one of the co-founders of reCAPTCHA, the squiggly letters that you type in when you sign up for a website. And at Facebook, I've worked on our infrastructure team, working on performance, reliability, and on open standards, like working with the web standards to make the web faster. So let's start with just a quick introduction of what we're going to talk about today. So to start our presentation, I'm just going to give a little bit of an introduction to what the Libra Association's mission is, why it was created, what problem it's trying to solve. Then move to talk about the Libra blockchain, the technology that underpins this payments network that the association is building. And finally, talk about one of the many cool things that we're working on, which is the Move programming language, which is a new smart contracting language that's designed to make it easier and safer to program financial applications. Okay, so let's start off just talking a little bit about what Libra is doing and what its mission is. So around the world, many people lack access to financial services. There's 1.7 billion adults globally who are unbanked, yet 1 billion people have a mobile phone, or 1 billion of those people have a mobile phone, showing that there's a lack of access to financial services even for people who have access to the technology that they need to access it. And $25 billion a year is lost by migrants due to remittance fees. And you don't actually have to go far to see the kinds of challenges that people have in the expense of the financial ecosystem. As part of this project, when I talk to folks, I often talk to them about their experience with payments. I was talking to someone who was saying about how they sent money back to their family, and was asking, was it easy, is it hard? And they said to me, it's really easy. All I have to do is I have to go to the store and pay a 5% fee. So as technologists, we should all be a little uneasy that someone has to go to a physical store to send money, that they have to take a 5% fee for changing what is essentially a number in a database. And so this is really the problem that the Libra Association is trying to solve. And it's solving it through building a new global payment system that is powered by blockchain technology and builds on the distributed trust and distributed governance that comes through using blockchains. And so it's run by an independent Libra Association, which is designed to oversee the development and the management of the network. It's fully backed by a reserve of fiat currency. So it builds on top of the distributed governance that comes from existing currencies. And it's built using open source technology, using the Libra blockchain that builds on top of, that sort of built on top of a modern system. So, we should all be a little uneasy that as technologists, public key cryptography has existed for many, many, many years, and yet we still type 16-digit credit card numbers onto websites, and that's sort of the state of the art. We should be a little uneasy that we use financial systems that if one computer crashes or loses data can go down or become unreliable, despite the fact that technology like Byzantine fault tolerance has existed for many years. And so this technology and this approach is really designed to bring a more modern approach to these financial systems. Okay, so how does this help the person that's paying a 5% fee, right? It's all great, but how does this help that person? And the key here is really that Libra, through offering this blockchain, offers both users and developers direct access to a financial infrastructure. So users don't have to rely on an intermediary to store their funds. There's nothing wrong with intermediaries. A lot of us use them every day, and many people are comfortable with them. But there are a lot of intermediaries that don't necessarily focus on financial inclusion. And a lot of the people that would want to use the system may not have access to such an intermediary. And so Libra offers people direct access to the platform and thus creates a more inclusive system. And developers can leverage a robust platform that takes the hard parts out of financial programming, that creates a solid foundation for them to focus on building the applications that they want to build. And by enabling more developers, you enable people who can then, then provide services for people who are not included in today's financial ecosystem. So let's move to talk a little bit about the details of the technology that underpins the system. So the Libra blockchain is a Byzantine fault tolerance-based blockchain. So like most blockchains, you have a client, an end user of this ecosystem that submits transactions to a network of validators. A leader proposes a set of transactions. You use the magic of Byzantine fault tolerance to come to an agreement on a consistent ledger of transactions, and clients can observe this consistent ledger so that they can understand what the current state of the network is. So very standard, very typical application of this type of technology. So when I talk to people about what the Libra Association is doing and what strategy it's used, a lot of times I get this question, why don't you use a database? What's wrong with databases? Why aren't you using them? And at the end of the day, I think it's worth remembering that blockchains are a type of database. They're a versioned database that stores data that changes over time. They're authenticated, but at the end of the day, they serve a similar function to a database. And so this diagram just kind of gives a little bit of an interpretation of that. Talks about how the Libra blockchain tracks a set of states. And so in this case, Alice and Bob have accounts that are on this state. Alice has 110 Libra, Bob has 52 Libra, and there's a transaction that says send 10 Libra from Alice to Bob. And this transaction gets ordered using Byzantine fault tolerance and gets put onto the ledger and correspondingly changes the state of the blockchain so that Alice now has 100 Libra and Bob has 62. And so this is, if you showed this to someone who was building a traditional financial ecosystem on top of a database, they'd be like, okay, that makes a lot of sense. And so the blockchain technology is actually derived from that sort of approach. So in our system, like most blockchains, we use Merkle trees to efficiently encode data. And the validators sign this ever-growing Merkle tree. And so this is something that's a little bit different from typical blockchains. So in typical blockchains, you sort of have this linear linked list of blocks. And we took a slightly different approach where instead of signing a connected list of blocks, you sort of sign this just ever-growing Merkle tree. And what this does is this, unlike traditional blockchains, allows you to efficiently authenticate not just the current state, but historical states, and using a logarithmically sized proof. So this is sort of a tweak to the traditional approach. Like most blockchains, each state that we have, or each transaction that we have sort of corresponds to an entry where we store the transaction itself. We store a sparse Merkle tree that has the ledger state in it. We store we also store a list of what we call events. And so for folks who are familiar with Ethereum, this is somewhat similar to the concept of logs. They're things that happen during the transaction. So we talked about how there's a database of state, but when you're looking at things like during this transaction, what transpired was that there was a payment of 10 Libra from Alice to Bob. An event tracks something that happens, whereas state tracks sort of what the current or previous state of the universe was. So altogether, this system provides a few key properties. The Byzantine fault tolerance system provides safety and liveness. So as long as 2/3 of the network is operational and honest, you can get a consistent view of transactions. You'll be able to accept new transactions. You get efficient state authentication. So as I talked about, not just the current state, but you can also authenticate historical states. sort of historical ledgers of what events happened when. All of these queries can be efficiently authenticated just using the current root hash, and all in logarithmic time, or in logarithmic space. You get a full audit, so you get to see all of the transactions that have transpired and the sort of the evolving state of the network. And finally, you get this property that brings us to the move language, which is the ability to safely represent assets and isolate programming. So to explain this, I'm going to move on to talk about what the move language is, why we designed it, and how it's different from some of the current approaches. So let's just kind of zoom in a little bit to the previous diagram that we had and focus on what's happening when you have a state transition. So a replicated database is a type of replicated state machine. Everybody is seeing the same transactions and should see the same evolving state over time. So if you have an initial state 0 that everybody agrees on, and you have someone that can help you agree on transactions 1 and 2, then, and you do this through Byzantine fault tolerance, then if you agree on the initial state, you agree on the transactions, and you agree on what transactions mean, then you also agree on what state 1 and state 2 are, right? It's sort of a basic inductive logic that allows you to see what the following states are. So how do you handle a state machine in a financial system, right? Because a lot of us are used to programming state machines when we're in full control of the system, and we're used to programming and saying, okay, Alice can send the money that she has to Bob, but she can't just take money out of Bob's account. How do you handle a programmable system that does this? What you need to do is you need to make sure that you have a language or a scheme for representing transactions and how they evolve the system. And this is what all blockchains do, ranging from Bitcoin to Ethereum. They have some sort of way of defining what a transaction means and what transactions are valid. So what do you need to have a blockchain programming language? What are the fundamental requirements? And these aren't novel. These are things that I think a lot of systems have followed, but I think is useful as a frame of reference. What do you need to have? Clearly, you need to have something that's deterministic. So if the blockchain transaction could read from your local file system, then everyone would see different states because they have different local file systems. And you can't have things like random number generators or hash tables that are inconsistent depending on how the machine felt, what the iteration order would be. So you need to have a language that's predictable and that has the same effects given the same initial state. So you need to make sure that you have a type and memory safe system. So if you were able to do a smart contract in C and just able to sort of manipulate bits in the blockchain, you could go and change arbitrary data in there. You could add money for yourself. You could sort of do whatever you want. So the transaction needs to be something that is that really is contained and only allows you to take valid actions, only allows you to create things that you should be able to create. And you need some sort of metering. You need some framework to ensure the responsible use of resources. Typically, if there's a public system and there's no consequence to taking resources, somebody will take all of them. And so, from this insight, you really have the concept of gas metering to be able to measure what the cost of executing a smart contract is. Okay, so I've really just focused on some of the basics of smart contracts. And this is stuff that already happened before we did Move. So I think you could, Solidity meets these requirements. And whenever you're creating a new programming language, people kind of give you a weird face. Because they're like, why are you doing that? Do you really need to build a new programming language? And we saw a lot of that as we were thinking about it. I really wanted to write down, okay, what do we want to do on top of these core requirements? And so this sort of inspired the key requirements from Move. And so the idea of Move is to build a language that's really designed to be something that fits with the paradigms you use when you're programming with money. And to program with money, you need to, money is something that you can't create or destroy just on your own. It's something that is, sort of is limited. And so we created this concept called a resource, which is a safe abstraction for representing things that are like money. And so on top of that, we built a system of generics to allow a, sort of a flexible programming environment, allowing people to reuse code across different types of resources. And one of the things I think we did, which is different than a lot of techniques that blockchains have used, is we really forced ourselves to eat our own dog food. What this means is that everything in the Libra blockchain is represented using Move. So a Libra coin is a Move resource. There's no magic, hey, this is sort of money and there's a special programming abstraction for that. The Move language is as agnostic to what is built on top of it as most mainstream languages that we work with. And beyond just representing the Libra currency itself using Move, we also represent things like what signature needs to be present on a transaction to authenticate it. That Alice needs to sign her transaction, Bob can't sign it. We represent the idea of what is the current validator set, what logic is allowed to change that validator set. And so by forcing ourselves to really dog food Move in the core of the language, we were focusing on building a language that is safe, that enables programmers, and also enables flexibility to allow us to express these concepts in a way that is that's sort of easily tweakable or changeable. So Move was designed to also be a language that's safe. And so it has a bytecode verifier that enforces properties such as resource safety and reference safety and type safety. It only crashes or fails to validate a transaction for predictable, unexpected but defined behavior, such as being out of bounds of an array, having a division by zero, overflow. It's designed not to have static or to have dynamic dispatch. All of the call sites are static. And we've really designed the language from the ground up to support formal verification. So this is where we benefit from having a lot of really smart folks in the team with a lot of cross-functional, cross-disciplinary experience who have sort of helped us figure out what we should do to make the language easily support formal verification techniques. So keeping local and global states as trees, limiting the amount of mutability, making sure that references are transient, that you can't just store them in global storage, having an acyclic dependency graph. So we've really designed the language to be expressive, but also one that's easy to analyze. And I think if you had to sort of describe Move in a nutshell, it would be about the idea of having resources that are scarce and that represent assets and authority. So assets are things like Libra coins that are, sort of objects that we're used to in physical objects. You can't just duplicate them. You can't just create them from scratch. You kind of have to transfer them around. And authority is slightly more nuanced, where you can have certain, pieces of code that are authorized to do something. So someone's Libra account might be authorized using their public key and a signature on that public key. And that is an authority that could, in theory, be transferred that they can duplicate, but that no one else can duplicate. And so, again, to put Move in a nutshell, it's really about how do we represent this sort of paradigm in a programming language. So with that, I'm going to kind of show some examples of Move to give people a feel for how it works. So just getting really basic. If you have this example function and you have a Libra coin resource that has an integer that represents how many Libra coins are inside of that resource, and you have a function that takes a coin as input, you can't spend it twice. You cannot pay it to two different functions. It's an error because you've already used that coin. As I think just from this example, you can sort of see where a novel approach to handling resources can be useful. I think if you sort of think of yourself as a programmer who'd only seen C before, and you see a language, Python or Java or whatever, and you're like, oh wait, you can't just cast this type to a random other type. You have to keep it the same. To me, this is sort of the aha moment here, where you're like, okay, wait, you have an object that represents, a resource that represents money, and you can pass it along, but you can't spend it twice. So you also can't get around this by trying to duplicate the resource. You can duplicate things like integers that are, primitive types that are fine to duplicate, but resource types can't be copied. And so, unlike other applications of linear types, you have to use a resource exactly once. So this prevents programming errors where you accidentally forget to use something. And so I think if you think about some of the types of bugs or just difficulties in programming that people have had with smart contracts, this language can help address some of those core issues. And this is why we sort of, to answer that question of the funny face that people make at you when you create a new programming language, this is really what inspired us to say, okay, there's something here that's a need that's not met. And it's why we built the Move language into the core of the Libra blockchain and have really dogfooded it as we've built our system. So if you're curious about this, there's some resources you can go to. There's a Libra developers page that shows you there's a paper on Move, a paper on the Libra blockchain. The Libra website from the association talks a little bit about the mission of the association, how the members and how it's how it's organized. Called Libra, which is Facebook's digital wallet, that will be able to hold Libra. Has a website, calibra.com, so you can learn a little bit more about the plans. And then we'd love to have people here join the conversation. So we've got a forum where you can go and discuss the approach of the Libra blockchain. And the code for both the Libra blockchain and Move is all open source. Happy to accept pull requests from people. And the association is working on even a more formal governance system to accept Libra improvement proposals. But for now, issues and pull requests are very much welcome. Cool. With that, we have a little bit of time for questions. So I think that there's,
Can you repeat the question?
Yeah, so the question was really around sort of the, what amount of inspiration we drew from Ethereum and sort of how we view ourselves compared to Ethereum, and also talking about sort of sharding and multi-chain approaches. So I think like most technological systems, you look at what's out there and you're inspired by things that come before you. There's a lot of what's in there that's, a lot of Ethereum is inspired through Bitcoin. I think there's a very good heritage there of things. So what we did when we started this project, I actually broke one of the printers at Facebook, printing out so many papers, and really researched, okay, what's in the space, what's out there, what ideas do we like, and where do we see gaps? And so this is where you get things like having Merkle trees and using them to authenticate state, but choosing to use Byzantine fault tolerance instead of proof of work, choosing to build a new smart contracting language. And so to me, it's really about making the right decisions for the platform. I think that at the end of the day, different blockchains are built for different use cases. And the Libra Association is building this blockchain for the use case of financial inclusion and really focusing on people that their focus is really on having a financial ecosystem that works for them. And so that's where the sort of the genesis of the technical decisions that we've made comes from. So around multi-chain and sharding, I think that that's an interesting area of exploration. I think that one of the approaches that that Libra has chosen in contrast to other systems, I think, is being a little bit more sort of focusing on validators that have, sort of typical commodity, internet connections, as opposed to sort of a more pessimistic assumption. And so I think that for Libra, that's a little bit farther off, but it's an area that's really interesting to explore.
So you have a list of things you'd like out of a language, including an inspiration from linear logic. I think that Shane's Ivy also had this idea. Why did you decide not to use like Ivy?
Sorry, I'm not familiar with the language you're talking about. So.
Okay, fair.
Yeah. There were other questions? Oh, yeah. Oh, okay. I'm gonna get my exercise today.
Hi, you mentioned that Libra is backed by fiat assets. Could you please elaborate on that a little more?
Yeah, so the Libra is backed by a reserve of assets. So assets are only created when fiat currencies are deposited into the reserve. So you do need to have an entity that acts sort of as an oracle to tell you when that happens. And so I think you can look at other stable coins out there to kind of get a sense of how that can work, right? Where once you're on the network, you're able to do transfers within the Libra blockchain without going out into fiat. But in order to create new coins, you do need to put fiat currencies into the reserve, and it's always one-to-one backed.
Thank you.
People want to play with it now. If they don't want to play with Move, how stable is it? How easy is it to use?
Yeah, so I think that it's available to clone in GitHub, so people should very much feel welcome to try it out. It's evolving. Just as we're thinking about how to kind of move the network from prototypes and ideas. So just in a sense of timeline, the Libra Association announced in June, and so. Just sort of thinking about, okay, how do you go from that initial working version to something that's stable? And so, but the code is very much out there, very much welcome for people to play with. We've seen people who have gone really into depth on consensus, on Move. We've seen people who have tried out Move in different contexts, which I think is one of the really exciting parts of Move, that we've always intended it not just to be a language for the Libra blockchain, but to be a language for programming with assets. And so definitely, would love to see people's thoughts about it. And if you find that it's not easy, send a GitHub issue and tell us why.
Great. We have time for one or two more questions. Yeah.
So you mentioned that Move is designed to be amenable to formal verification methods. Are you designing any tools, or is there things outside of the Libra group that's being developed along those lines?
Yeah, so we've got a team of people that many of whom are in the audience here today, that are focused on figuring out the right kinds of tools to build. And so it's definitely not just built with the intent of formal verification in mind, but also sort of figuring out how we progress along that path.
One more question. Did you ask a question already?
So since Libra will capture hundreds of millions of transactions, right? Is privacy a concern or not?
Yeah, so I think that the Libra's approach really is to provide a core of the financial infrastructure, and it provides a lot of different options for people. So many people will access the network through intermediaries. As we talked about, we're not against intermediaries. We just think that people should have the option not to use one. And so all of those trade-offs will come with different trade-offs in the privacy spectrum. Our goal is really to make sure users understand what they're signing up for and what properties a blockchain provides them.
Can you talk a little about the Move VM architecture? Are you using some standard approach, or is it something new entirely?
Yeah, so I can talk at a really high level about it. It's a pretty similar approach to most other systems, where you sort of take a source language and you compile it down into a set of bytecodes. And the security properties of Move are provided at the bytecode level. So sort of similar to Java, for example, where object safety in Java is provided not by the Java programming language, but by the JVM bytecode. And so at the bytecode level, the virtual machine, which is what runs on the validators, is what enforces the safety properties of the system.
Great. Ben, so I think we're out of time.
Thank you very much.
Thank you so much for coming. All right, it's great to see all this progress. Okay, so our next speaker is from Forte. Is Brett here? Brett, where are you? Yes, thank you. Yes, please come up. Yep, so all yours. So Forte is another really exciting applications for blockchains, and I'm looking forward to your talk.
Thank you. Yeah, sorry, I'm just, okay, good. Oh. Is this, you need to mirror it. Okay. Mirror and pivot. Yeah. Oh, I see. You're saying it won't show up as an option. Yeah. All right. All right. Thanks everyone for being here. Let's get started. So I am Brett Seiler. I'm part of a project called Forte, and we are aiming at equipping the game industry with tech and tools to run portions of their game economy or even the entirety of their game economy on blockchains. So this is a unique set of constraints compared to what a lot of people are trying to build on blockchains today. So we are game experts. There are definitely people more expert than us on some of the topics that we're going to cover in this presentation. But what we want you to come away with is our best sense of a plausible path to get game economies running on blockchains. So, all right. I've done a couple talks on sort of double-clicking on unique stuff about the game industry and its and its reasons and motivations to even consider this. It's a very big industry. It's $150 billion a year right now. It's grown in the last 2 decades primarily by the free-to-play business model. If you're a citizen of Earth, there's roughly a 1 in 3 chance that you play games. So it's a huge audience. And so if you want to go a little bit deeper on some of our motivations, I just wanted to point you guys at some of this previous work that we've done. In particular, if you really want my best attempt to communicate to the game industry directly about why they should consider this, we published a series of blog posts on Medium called Free to Play Isn't Free Enough about this time last year. So I'm going to kind of leave all that in the dust and move into how we're thinking about markets and tools suitable for game developers to use. So games are, if you're not familiar with the way they're built or managed, they have a kind of dizzying array of different item types and just a single game might have hundreds or thousands or even tens of thousands of different distinct items. And oftentimes these can be composed into each other. You can use one type of item or currency to upgrade another type of item or currency. And this is good context to come into the conversation around blockchains and how to facilitate markets appearing and providing liquidity around these kind of assets. So there's a lot of info on this slide. I'm not going to read through all of it. What I really want you guys to take away from it is that in the real world, that you see market designs tailored toward the kind of assets that they're transacting and what the participants in the market look like. And some of that kind of maps onto what you see in games, but when you look at the characteristics of interacting with some of these other market designs, it's pretty quickly clear that they'd be an incredible user experience challenge to impose on authors of games or game designers. Kind of get back to this, but not every Candy Crush player wants to participate in an auction, and you're going to have all sorts of challenges if you're waiting for dual coincidence of wants across this super disparate item base and maybe, again, even just a single game. So we want to drill down a little bit more past that. This is kind of like, a rough approximation about like how these categories of, fungible, not fungible, divisible, indivisible might map onto market models if you're just looking for analogs in the real world. Okay, so we think the crux of the issue to kind of narrow in on, there's all these market designs, there's all these assets. I think the crux of the issue is really one of user experience. User experience to meet the benchmark of most modern games. Again, big industry, but you might have, you have individual games with, in some cases, over 100 million active players. You're not going to reach that kind of scale if you have a high friction user experience around what it's like to play the game, invest in the game, improve your things in the game. So low friction UX is really key. And this kind of points us toward automated market makers, which we're going to get into. But again, I think if you're really interested in the technical details of what's possible with blockchains and being a little quick to try and map that onto what would make sense for games, it's easy to kind of kick the can down the road on user experience challenges. But again, we're focused on how to get the game industry to actually use this stuff. So it's first and foremost in our minds, and it's often the first question we get when we're talking to people about it. So any solution that I think we propose for game developers to actually adopt, it's got to just work. The experience has to be at least very close or comparable to what people experience today in putting real money into these games and in exchange for totally virtual goods or services or items. Okay, so we think we have a couple sort of twofold step toward making this work. So I'm going to jump into the first one. If we had the option to boil all the items that might appear in an individual game down to a single game currency, which might be a blockchain, if we had that option for a game designer to sit down and say, I want this gauntlet for this character, and game designers actually think about the relationship between the various currencies in their games and items that they might want to motivate the user to acquire or improve. So they're kind of thinking about these relationships, and sometimes there's in effect an exchange rate already between a lot of these, and that's part of updating and rebalancing a game design is sort of revisiting and readdressing how balanced those systems are. But starting with even just a little bit of collateral is kind of it gives us an interesting way to try to do automated market making around items in games. And it gives game designers a new set of tools to think about how they want to motivate players to achieve whatever goals they're set in the game or acquire the most interesting stuff. And they can interact with an automated market maker to find liquidity instantly. So that's what we're going to get into here next. So automated market makers have a lot of, there's a lot of reasons to choose them through a game designer's lens or a game developer's lens. Immediate liquidity, really rapid price discovery, even where you might not have good signals from the market or a lot of trading activity. That's an interesting place to start, but it really kind of hinges on this idea that you have some sort of at least baseline price signal or floor on assets, and that's where the collateralizing every item approach we think is a promising path forward. So I'm also going to talk about token bonding curves a little bit, and in part not because, well, I'm not sure token bonding curves are actually really well defined, but my best attempt to define them is a fully collateralized automated market maker that's often also the issuer of whatever the good or the token might be. So starting there is kind of a good lens to think about how you want to design a market maker to match what sort of activity you expect to have in a market. And again, for games, some games will look at this from the perspective of already seeing a lot of market-like activity or being able to at least proxy their way into expected supply and demand for a thing. But new games don't have that luxury. They're really guessing until players get into the game and you really get to see activity. Okay, so token bonding curves actually, I think they're a really good way to start to think about how to do automated market design, because it's some of the thought experiments are really just like plain to establish. You can look at what if you had a different set of buy and sell curves that converged or diverged or tried to establish a fixed fee. You could set redemption limits, but the functional form for these market makers is kind of a wide open design space. There are limitations based on what's reasonable to compute and execute on chain, but there's already some interesting projects out there using some of these constructions, and this one sort of with the unicorn. You guys probably, I'm in an audience where I would assume there's a lot of people who know what Uniswap is. Uniswap fans probably don't. This is where I say there's a well-defined problem with token bonding curves. Most people, I think, don't think of Uniswap as a token bonding curve, and I actually think that's appropriate because it's not fully collateralized as an issuer. But really useful AMM, and it's really kind of leaning on some of the same constructions to have an automated market maker respond to activity in the market in a way that's deterministic. So again, trying to reason our way toward what good automated market maker design might look like for games, we can look at some of the functional forms that are common in token bonding curves and kind of see some likely mismatches to what you might see in a new game or a new run of game items. Don't want accelerating price volatility with growth. Typically, you want something more, something that becomes more stable as it matures. And similarly, you don't want to try to bound the scale of your market before you, especially with something like a game, which could be 0 people play it or 100 million plus. So unless you have some foresight into what that's going to look like because you've already got a game and you're just trying to map these sorts of tools onto a market or marketplace-like behavior, really difficult to set up in advance. And a lot of people point to the sigmoidal functional form as likely a more natural, better fit for AMMs. I think good intuitive reasons to start there. So we'll get into that. But I think, going back out from this, I think, narrower conception of automated market making in token bonding curves and thinking about their limitations, whether it's front running or difficulty responding to changing conditions in the market. There are a lot of reasons to think about adding some complexity to address real problems. So this is just for illustration purposes, not something we're prescribing, but you can kind of, again, reason your way to the next step and consider what an automated market maker that can respond to other feedback signals from the market might look like. And pretty quickly, you're not like looking at 2D curves, even if you're thinking about a snapshot in time, you're looking at surfaces. You're seeing a lot of projects start to take this approach, but as you add parameters, it becomes more and more difficult to have a reasonable, visualizable construction. So, like most people don't think about what it looks like to visualize the most widely used automated market maker designs, Hanson's LMSR and the liquidity sensitive extension of it that Othman put out there. So let me back up a little bit. So this is a good place to start, we think, for reasoning our way from blank slate. You want to build a game, you expect some people to behave a way, but you really have difficulty setting up the parameters in advance to something that can respond more actively to the market and better mirrors the kind of growth and adoption and maturity cycles that you see in games. So we can't talk about AMMs without also talking about front running. This is kind of a top of mind consideration. I think like recent stuff happening in DeFi, but this is a structure that you see mirroring financial markets. We think for good reason, and the vulnerability in automated market makers to front running really comes only if they are pricing and settling a trade, both. If you separate the pricing from the settlement, then pretty soon you have some really realistic approaches to curb front running. So this isn't what everybody in DeFi wants. There's more friction here, but there's also more compliance and there's higher confidence that you can have an automated market maker drive a ton of activity in any market and see results that participants are happier with. All right, so going a little bit further and thinking about how as a game designer whether you've constructed the right AMM for your project, or whether you've also, if you've got a game currency and it denominates most of the items in your games, and you have an AMM to sit between them, or to facilitate, fiat onboarding and offboarding, you have different problems. But to evaluate AMM design and mechanism design, there's a couple pieces of work that we thought were really valuable in our approach to just trying to ramp up on all this stuff, and that we keep coming back to as instinctually, and I think we're verifying this as we go, the right lens to approach this problem space. So the first is this paper Vincent Chia published in 2018. Kind of made some of the crypto Twitter rounds a little bit, but it's called Rethinking Blockchain Security, and it offers a framework called Presto for evaluating how well a network's designed. And the criteria are criteria here commonly discussed in some cases, but it kind of gives you as a designer of a system, and if you're making a game, you're making a system. You're trying to balance and get the results out of the system you want through a whole bunch of different levers, but really evaluating what might happen, you need to have clear goals. And one of the I think the more interesting last two rungs of the ladder in this Presto framework are the robustness and persistence qualities to network design. And there are definitely people doing good work thinking about this stuff in blockchain and this kind of intersection with blockchain and games. But we see a lot of design decisions that sort of stop at the algorithmic game theory verifications of what you can expect with agents or players interacting with mechanisms or something like an automated market maker. So we think the more useful and appropriate lens to view this stuff is complex adaptive systems. So a good deal of our team have backgrounds in applied math, and there's some interesting projects in the space taking this approach and trying to build technology and tools that offer designers of, again, whether it's AMMs or networks broadly, tools to model, simulate, iterate what might happen based on your network assumptions through this full spectrum of Presto goals for establishing network fitness in a way that doesn't assume anything reasonable about agent behavior. You have statistical noise, you have adversarial and irrational actions, and real-world systems typically have to endure at least some of that. And this is where those last couple of conditions of Presto are really valuable. Like, how robust really is the network when people aren't acting rationally, when there's just randomness and noise in the system? And if the system gets way out of whack, and out of its sort of desired equilibria, does it have any ability to recover? Is there a way where you can look at a system broadly enough and add to the design or add mechanisms that prevent the system from getting so out of whack, from getting it into a state space where it can't recover? So we think this is a really valuable approach to thinking about these problems, and there's some really, I think, good work getting published, and I'll highlight some of that in a moment. And the kind of reach past having that lens, having some tools to do more rigorous mechanism design and test it under conditions that are not perfect, that include randomness and adversarial agents. There's a rich body of research and tools to borrow from other fields of engineering that look a lot like this. And under the right conditions, you can really apply a lot of rigor to not just having a design that works, but having an optimal mechanism of all possible designs available to implement. And we just think it's a really valuable frame of mind. So if there are, if any of you guys are kind of like just blockchain curious but have some of this in your skill set, it's a point in a couple directions. So, all right. So this is kind of like a preview of what we hope develops in the space and what we hope to contribute to over the next couple of years in building these systems for games. I mentioned there's some really impressive people doing work in this space, including looking at modeling systems, including modeling mechanisms, and taking a complex adaptive systems approach, and also just like thinking about automated market makers and considering how they can be parameterized and what still works on chain and what is suitable to what market. So this is a sample of we think like people that have helped inform our thinking a lot, and people we think are really contributing to understanding how to do this stuff better. So thanks to, it's a fantastic community. Thank you for publishing your work and helping us think better ourselves. Right.
So you mentioned that you're kind of targeting games that have 100 million plus users. So is there going to be a scalability issue? And
Absolutely, yes. All kinds of we have, I think we've talked publicly about a handful of games that have used our platform and have players transacting on the platform today. And I think at least one or two are games that are too small for any of you to ever heard of, and they're already big enough to have scalability issues, even compared with other interesting examples of high use that you see on blockchains. So yeah, we definitely got scalability challenges ahead of us, and that is not my deepest area of expertise. Okay. So I'll punt if we get much deeper there. But
so any other questions about the economics of games? Great. All right, Brett. Thanks a lot.
Thank you.
All right, and our final talk of the session is going to be another blockchain called Celo, and we're going to hear about light clients and such. Yep.
Thank you, Dan. Hello, everyone. My name is Marek Olszewski, and today, along with Michael Straka, we are going to be talking about Plumo, which is Celo's ultra-light client protocol. And this work is a joint work with Ariel Gabison, Iran Tromer, Kobe Gurkhan, Filip Junakovic, Asa Oynes, and Sai Vesely. Awesome. Okay, so why Plumo? And Plumo, by the way, stands for feather in Esperanto. So I hope most people here are familiar with this graph. Chain sizes are growing. This is a graph of the Bitcoin chain size over time, and it has continued to grow a lot. We're now at 260 megabytes. The Ethereum graph for this is even bigger, almost 1,000 times bigger. We're at 230 gigabytes. At these sizes, I think it's ambitious for any kind of crypto enthusiast to spin up a full node and kind of sync with the network and kind of validate transactions. All the more so if they want to use a resource-constrained device. On the flip side, these kind of resource-constrained devices keep growing in popularity. Here we have a graph from the Ericsson Mobility report that just came out last November. We have officially passed the 8 billion mark for the number of mobile devices that have active mobile subscriptions in the world. That is a staggering number. 6 billion of these are actual smartphones as well. And as you can see, almost half of them have LTE connectivity today, and that number will only grow in the future. Switching gears a little bit, there's also been a lot of talk about central banks getting really excited about issuing their own digital currencies. This is a graph from a paper released by the Bank of International Settlements last month that shows a number of countries that are really interested in exploring creating their own digital currencies, their own CBDCs. So right now there are 54 countries that have committed to or have actually already started exploring creating these own chains. Many of these chains are going to be likely private chains that will have to communicate with other chains so that people can trade across countries. Hopefully they'll also try to bridge to public chains so they can tap into all the exciting DeFi that's going on these public chains. But in order to do this, you have to actually verify the state of another chain in a smart contract on the first chain. And smart contracts, as everyone knows, are much more resource constrained even than mobile devices. And so this presents another interesting challenge. And so Satoshi, to her credit, has already been thinking about this for a long time. If you go back to the original Bitcoin paper, there was a section titled Simple Payment Verification, where she outlined a like client protocol that lets like clients sync easily with the chain. The protocol assumes that there isn't a 51% attack on the chain. And in this scenario, the longest chain, the one with the most proof of work done on it, will in fact have only valid state transitions. And so as a like client, you simply have to connect to the network and download all of the headers since the Genesis block, verify all of the proof of work, and at that point you can use the last header, use the last Merkle root commitment to verify any Merkle proof that any full node sends you for any data that you might query it about. And so this is pretty simple and it works quite well. But if you look at the chain sizes today, for Bitcoin, this means that you'd have to download 47 megabytes of data. And for Ethereum, it's even more, 4.4 gigabytes of data just to do a like client sync with the Ethereum network. That is simply too much data to build a fully permissionless, decentralized kind of mobile wallet. Say you wanted to do something that maybe was a permissioned version of Venmo, permissionless version of Venmo. You wouldn't be able to do that with today's like client protocols. And if you try to do this on a proof of stake network, these numbers would actually be even higher because with proof of stake networks, your block times tend to kind of decrease, and so you have more headers than in proof of work networks. And so you can't really build a mobile app. It's hard to build bridges that are fully permissionless. BTC Relay famously built a bridge, or not a bridge, but was verifying Bitcoin headers on the Ethereum blockchain for a while. This was working well until gas prices went up, and then the cost of doing this became too onerous. And I think I checked the other day, it hasn't been syncing since about 500 days ago, so over a year ago. And so this as well is really hard to do with the current like client protocols today. And so there's been a lot of interesting research around this. A lot of people have identified this as a problem worth solving. And on the proof of work side, we've had a lot of really great innovation. Both the NIPAPA work and Fly Client have used probabilistic arguments to allow you to download less than all of the headers since the beginning of time. With Fly Client, you can download something that's proportional to a logarithmic amount of headers. For Ethereum, this comes out to about 500 kilobytes, which is much, much better than the 4 gigabytes. And so really exciting work, but unfortunately, it only applies to proof of work networks. It's hard to bring this to a proof of stake network. On the proof of stake side, Coda has done some really interesting work on this front as well. Through the use of recursive snark composition, they construct snark proofs that not only prove that a particular header or block is part of the chain, but that the whole block is valid. This is really exciting, but strictly more than perhaps we need for a typical like client. And it comes with some trade-offs. Number one, I think it's hard to actually build smart contracts into a chain that's doing this. You'd have to have the smart contract language be written in a DSL that's very snark compatible. That's one limitation. And then the choice of curves that you need to use in order to construct these proofs efficiently have a number of trade-offs that Michael will talk about in a few minutes. And so what is our approach? What is Plumo? Plumo is the like client protocol for the Celo proof of stake network. And if you're not familiar, the Celo proof of stake network, it really looks a lot like, or has a lot of similarities to something like Cosmos. At a high level, end users will stake or lock up a digital asset, and then using that, they will cast votes in a d'Hondt election to elect a number of validators who then secure the network by using PBFT consensus. And these validators, they basically sign off on a particular block by attaching a signature to the header of each block. If that header is for a block that contains a valid state transition, then they'll sign it and they'll distribute it through using the PBFT consensus protocol to all the other validators, who then collect them all and attach them to every header. And so now if you wanted to implement a like client protocol that would sync with such a network, it would be pretty similar to the SPV algorithm we talked about before. You fetch all of the different headers since the Genesis block. You can use that to then run Merkle proofs when checking state from full nodes. But instead of checking the proof of work at each header, you're instead checking something else. You're instead checking that every block has 2/3 of the current validator set signing off on it. And on top of that, you're also keeping tabs of any validator set change that could have happened due to one of these elections. So in Celo, a block is only valid if it contains an election. The election results are stored both in the smart contract, but a diff of the validator set changes is also stored in the header so that a like client can quickly, while zipping through these headers, keep track of any changes. And so this allows you to recreate kind of that standard SPV style like client, which is nice, but it's still pretty slow and still requires a lot of data, especially again for a proof of stake chain where the block times are actually much smaller than for proof of work chains. And so Plumo improves on this with 3 new innovations. Number one, it introduces the concept of epoch-based syncing. And so under Plumo, a validator election can only happen on the last block of an epoch. An epoch typically lasts a day, which means that within that day, the validator set cannot change. So this means that you can actually sync any header in any order. You can skip headers entirely because you know that the validator set won't change. And so you can easily verify any header by checking that 2/3 have signed off on this. If you want to sync from before the epoch, you simply have to download the last header of each day where the validator set can change. And so this means that, say you're syncing from the beginning of the network, you only have to download the last header of each day, or 1 header per day. So for a network with 5-second block periods, this is a 17,000 times reduction in the amount of data that a like client has to download. So it's already pretty significant. Next, Plumo uses BLS signature aggregation to aggregate all of these signatures from all of these validators, hundreds of validators, into one constant size multi-signature and an efficiently encoded bit vector of the validators who signed that particular header. And so this gives us another 10x reduction in the amount of data that a like client has to download, and makes it much more scalable because we can add validators more easily without overly impacting the size of the chain. And finally, since we wanted to go even further than this, since we wanted to have a mobile experience that rivaled centralized applications like Venmo and other ones that you're familiar with, we wanted to reduce this even more. And we do that by using snark proofs that effectively prove this like client protocol that I just described, checking the signatures of the last header of each epoch, and checking and updating the validator set changes so that a full node can do this proof, can run this computation, share it with a like client. These proofs are oftentimes only around 500 bytes in size, allowing these like clients to sync with the chain near instantly, again, bringing back that experience that many of us are used to with centralized services. And so for the rest of this talk, I'll hand it over to Michael, who will jump into more of the snark-related stuff. Thank you.
All right. Thanks, Merrick. So now we're just going to do a bit more of a technical dive into how we can achieve effectively a light client that will verify the correctness of a validator set using snarks. So what really are we trying to verify in each epoch, which recall is Recall is once per day and is going to encode the validator set difference, so the change in the validator set that occurs in that epoch. It is also going to have a multi-signature, which we can use BLS signatures to aggregate every signature of any validator in the previous set who has signed off on the new one into one signature, and then use a bitmap stored in the epoch block to recover the correct aggregated public key. And we can also then check in the bitmap, did more than 2/3 of validators in the previous set sign off on the new one? So how might we try to do this using snarks? Well, the logical structure of the proofs that we're talking about here are inductive. And because they're inductive, they are naturally recursive. So a good first approach might be to use recursive proofs. And what this means is that we can create a proof pi I attesting to the validity of the ith validator set corresponding to the ith epoch. And that proof pi I will also attest to the validity of all I-1 proofs. If that sounds magical, it kind of is, but that's how recursive proofs work. So here we have an NP relation R, actually a small abuse of notation because we're making it a function and not a set. I apologize if there are any complexity theorists here, but we have the public input X, which the verifier is going to receive, and also private input W, or witness. The public input in our case, per epoch, only needs to be the previous validator set and the next validator set. And then the proof is going to attest, given that the prover has access in the witness to the multi-signature, it is going to generate a proof attesting to the fact that the transition from the last set to the next validator set is valid. Of course, we can also make this even better. Instead of attesting to the validity of one validator set per proof, we can just kind of batch them together into one NP relation or one circuit in our actual snark construction that will then verify many epochs, such as 180, or about the equivalent of 6 months of validator set transitions, which, assuming honest validators, is basically equivalent to validating 6 months of chain data. So if we do this, there's basically 2 ways of instantiating proof recursion at the moment. One is using the MNT curves, which are known to be pretty large, about 750-bit base fields, and that's going to make our normal light client that Merrick was just describing a bit more inefficient, because you're going to have to download public keys if we use these curves for a signature scheme that are about twice as large. The other method, which is very recent, is to use half-pairing cycles with Halo, which is a new argument system that some of you may be familiar with. But it's still very recent work, and we've chosen to take a bit more of a conservative approach with making sure that we have extremely good security and are relying on battle-tested and known argument systems. In particular, we've chosen to use Groth16. So how might we do this without relying on proof recursion? Well, as I said, the proofs that we're talking about have a very natural inductive structure. And so we can really just need a way to link them together. And in fact, we can introduce what we might refer to as a compliance function, T here, which will simply take in the public inputs of 2 that are used to generate 2 adjacent proofs, and return 1 if, in fact, it is valid for those two proofs to be next to each other. And really what I mean by that is that the last validator set of the first proof is equal to the first validator set of the next proof. So in fact, each proof is simply attesting to the fact that there is a valid path from the first validator's set that the proof is considering for over 6 months. There's a valid path from that to the last validator set over those 6 months. And if you're a verifier on, say, a mobile phone, all you need to do is download those two validator sets, or rather their hashes, as a performance optimization, and the correct Epoch index that we're at, and then you would need to verify one proof for every 6 months, and potentially less if, depending on how much checkpointing is used on chain. So what do we actually need to verify in these proofs? Well, we're verifying BLS signatures. And what that means is that we're going to end up doing elliptic curve arithmetic, in particular pairing checks that are shown here, inside of an arithmetic circuit. So this basically means that we need to do arithmetic in the base field of whatever elliptic curve that we're using, but in an arithmetic circuit that is using a modulus of the size of the elliptic curve itself. This is extremely expensive and has a logarithmic blowup in the size of the modulus that you have. So hundreds times blowup. We can solve this by doing what almost amounts to a depth 2 recursion. So finite depth recursion, where we have one elliptic curve, in this case 377, which is the curve we use, which is found by some really great and talented people behind the Zuxi paper. And they also have a really amazing Rust library for snark construction that we've been very happy to use. But in their work, they found a curve 377 such that there's another curve, SW6, with a size that is the same size as the base field of 377. So basically what this allows us to do is to compute all of this elliptic curve arithmetic and pairing checks inside of SW6. Instead of, while still using 377, which is a smaller curve for our signature scheme, so that the public keys we store on chain are still reasonably small. Now here, we also need to compute a hash function. So there's been some really exciting work lately on a variety of algebraic flavor hashes that are going to be, well, we know are much more efficient inside of arithmetic circuits than traditional symmetric cryptography. But it's still not entirely clear how cryptanalysis on these hashes are going to pan out. I think, in fact, just yesterday, I believe a new attack was announced on NUMSI, and that's been around for a few years already. So instead, we've chosen to hedge against any new attacks that might come up by designing our own hybrid hash function, half of which is just a Peterson hash, which is algebraic, but does not output random-looking output, and can be evaluated in SW6 for the reasons I was just saying. And the other half is Blake 2x, which is going to take in the output from the Peterson hash and give us output which is now compressed and smaller, so Blake 2x, which is normally very expensive, will be cheaper. And that's now going to give us a random looking output for our hash to curve algorithm that we need for BLS verification. And then we can just compute Blake 2x in 377, which is a more efficient curve with basically depth 1 recursion. So this is the basic math behind what we're doing. How do we actually perform? So we rented one of the largest machines we could on Google Cloud, about 4 terabytes of RAM, ran it for 2 hours, cost us $12, and we were able to generate a proof that would attest to the validity of 6 months of validator set changes, or in this case, 180 epochs. And, we have some graphs here showing this, in particular the speeds of the 2 different circuits that I was just discussing. And we also looked at performance for verification. In particular, we're verifying Groth 16 proofs on mobile phones. We looked at a variety of phones, including the slowest phone we could find on BrowserStack. In the worst case, it takes about 6 seconds, which is still not that bad. And using more recent phones, proof verification is almost instantaneous. It's a fraction of a second. In addition, we've also come up with some estimates for what it would cost to do interchain interoperability, in particular between Celo and Ethereum, using our Plumo Lite client. And we estimate that it would take about 4 million gas to validate one of these proofs, which would correspond to a given epoch, and then about 20,000 gas afterwards for each transaction that we want to verify in that epoch. And this would come out to about $6, which is still pretty good. All right, that's all we had for you today. Like now we can open things up to questions.
Yep, pretty cool numbers. I have to ask, do you have a sense of how this would compare to the other approach, the Halo approach?
So I suspect that the Halo approach for our use case would be similar in performance. So I think it would be exciting future work, but right now it's still pretty recent.
Yeah, more room for development there. Great. Any other questions? Yeah.
How did you determine the duration of the epoch? And is there something within the protocol that can change that, or is it fixed?
Yeah, that's a great question. Yeah, Celo has full on-chain governance, and so all of these parameters are fully governable through basically a vote. And so, yes, it can change. We picked it to be a good trade-off between the sync time and the requirement on provers and like clients to verify those proofs, and the ability for the network to react to outages and generally just reorganize itself if new validators wanted to come online or other validators wanted to go offline. One day just really seemed to fit the bill.
Great. Other questions? Yeah.
Could you elaborate a little bit about the fact that you just, the validator set as opposed to the whole state? For me, a validator set just means who's validating the epoch as opposed to the state of like the counts, etc.
So what was the question, what's the difference between the state of the accounts and the actual validator set? Yeah, so the validator set is determined through that election, which is governed by stake that people put up and how they vote. And so in an honest running network, the validators would approve a state transition that represents a valid election. And so the output of that election would be kind of the new validator set. And by running those smart contracts and all agreeing that the execution of those smart contracts was correct, they basically agree on this new validator set, even if maybe they disagree with the fact that they might be getting kicked out, for example. And then for that block to be valid, you also have to include the diff of that validator set in the header. And so again, through BFT consensus, all the validators agree that that diff is correct and represents what actually happened in the election, and only then will effectively sign off on the block. And so if you do that, then you have this nice property that a like client doesn't actually need to verify the state of each account that was voting for these validators. They just need to verify that the existing validators agreed that the election was fair and correctly executed.
Cool. All right. Thank you very much. Fantastic. All right. So we have a break now until 3:30, and at 3:30 we'll resume with the snark session.
says how much time I have?
I think, if not, I'll give you minutes.
Okay, yeah, you can show with your hand.
Yeah,
5 minutes
exactly.
before.
I'll give you the 10 and 5. Okay. So we're at the, I think, last session of the day. So this is already the last session of a jam-packed day, and it's a very exciting one. It's about zero-knowledge proof, and if you've been following the space, there's tons of development, and one really cool thing, actually, I think that is happening is that it always seems like there's a lot of different proof systems, but it turns out that they actually, in some ways, really work well together, and there's great abstractions that are happening where we can take different tools and plug them together, and we will see some of this in this session, and we will start with a talk. I think Starks were first announced 3 years ago here at back when it was BPace, and now they're ready to use for developers and deployed in the wild, and it's really exciting to see how far we've come in the last couple of years. Like the development of blockchains and development of zero-knowledge proof have really come sort of hand in hand, and one of the people who are responsible for that is Ali, who's going to give the first talk.
Thank you. Thanks very much for having us here. So I want to talk today about Starks for developers. So I'm from Starkware. Our mission is to bring scalability and privacy to a blockchain near you. Our product is the Stark Exchange scalability engine that is going to be coming to mainnet very soon. Our team size is roughly between 30 and 35 people. We raised 40 million in funding. And Starks and Starkware are famous for achieving high scalability. So we can, today with the Stark Exchange system, we can already settle around 9,000 trades per second on Ethereum. And for payments, we can do 18,000. We already tweeted about this, and this is in a system that will be going live on mainnet soon. We're now extending these capabilities to also service the area of non-fungible tokens. So this is most of what we're doing is about building things that are very fast and scalable and can deal with massive throughput. But that is actually not the focus of the talk today. So today is not going to be about scalability. Well, what is it going to be about? It's going to be about snailability, or slowness, actually. And I want to present something that the takeaway message is that this is something that is very useful. It's very simple in terms of the interface for developers to use it. And it's actually ready for mainnet. And the main sort of reason we're describing it here is we'd like to talk to developers of L1 and L2 who might want to consider using this a very simple functionality that is also very useful. So let's talk a little bit about the concept of warping time using crypto. And one of the first examples of this goes back more than around 25 years ago to this very fundamental work about cryptographic time lock puzzles. It's a work of Revest, Shamir, and Wagner. And the concept is one of using crypto in order to create the analog of a sealed envelope that automatically opens after a predefined amount of time. And you can use this, for instance, for paying your monthly installments of your house rental, right? That's one example. You could also use this in an auction where you need to allow bidders to put in a sealed envelope that opens after some time in a deterministic way that they can't backtrack. So, and this has a lot of applications and has been described as very useful in a lot of contexts. And also on blockchains, it could be useful. Now, much more recently, there's this beautiful concept of a verifiable delay function that comes from the work of Bonnet, Bonneau, Bunz, and Ben Fish from roughly 1 year ago. And the image here is one of a roulette wheel that is spinning. And as you watch it spinning, you know that there will be some fixed randomness that will be determined by the laws of physics, but for a while, as you're watching it spinning, no one can guess where it's going to land. And because of that, you get some sort of fair randomness that no one, not the house, not the players in the game, can forecast, right? That's the concept. And VDF, a verifiable delay function, is the cryptographic analog of that. You use cryptography in order to generate this deterministic randomness that is unknown to all of the world for a fixed amount of time. So we have two different notions of warping time by using crypto. And the main message I want to point out today is that you can actually, using a Stark, you can actually get one building block that gives you both of these applications under the same smart contract. And this can also be transparent. So you can use it both for verifiable delay function, and you can use it for a time lock puzzle. And to me, when I heard this, this was a beautiful revelation. It's not my idea. It came from our amazing head of product, Avihu Levy, who's not here today because he's at the NFT conference in New York. But this is the concept that I want to describe in some detail today and sort of offer it to the developer community as something that might be used. Okay, so a good image to have when thinking about warping time in the way that we're going to discuss is to think about a jigsaw puzzle that we all recognize. And some of us love, some of us hate, but we all know what it is. So the main properties about a jigsaw puzzle are that if you see it made up and you really want to mess it up, it will be very quick to disassemble and sort of completely mess it up, right? And it's a lot of joy to do that, especially if you're a young child. Now, it's much more painful and arduous to actually put it back together. But once it's put back together, there's only a unique way that is correct, and you can easily verify it. So those are three important properties. And from this, you can get two different applications if you have this concept of a jigsaw puzzle. So suppose you want to get a verifiable delay function. So you want to do this analog of roulette, something that will spin for a while, but then at the end, there'll be randomness revealed, where the randomness is actually fixed at the start of time, just no one knows what it is. So here's how you do it with a jigsaw puzzle. You take a big blank square, you sort of make the contours of a jigsaw puzzle, let's say with 1,000 pieces, then you cut it out, so it's a big blank white piece of paper. Now you just scramble it up, that's very fast, and you take each piece that is completely white, and you toss a coin and you write the output on it. And then you publish the puzzle, and now the delay starts, right? So what happens is that it will take a lot of time in order to get the puzzle in the right configuration, and then you can read off this string of randomness, right? So the randomness is actually deterministically built into the start of time, right? Once you finish tossing the coins, it already determined what the string of randomness is going to be, but it takes a while for everyone to figure it out. So you get this delay function, this randomness that is delayed, the analog of a roulette wheel that is spinning. But with a very small twist, you can actually get a time lock puzzle. So you do the same process. You take the blank white paper, you cut the jigsaw puzzle contour, but before scrambling it, you take your secret, let's say it's some secret key, and you write it on each consecutive piece. Then you scramble it, and you show it to the world. So now you have created a time lock, because it will take a very long time for the world to fix everything back and discover what the secret is. So this one concept can give you both things, right? The verifiable delay function and the time lock puzzle. And that's what we implemented. And we want to offer it to the world. So we actually don't work with jigsaw puzzles, right, and pieces of paper. We do the cryptographic analog of that. And for that, you want something, you want a function, f, that is very quick in one direction, but it is very slow and sequential in the other direction. So by sequential, we mean that you can't parallelize it easily, right? It's in the paper about time locks, they give the analog of having a baby. So it takes 9 months for one woman to have a baby. If you have two women who are pregnant, you don't get a baby in 4.5 months, right? It doesn't parallelize. I hope Brian Bishop doesn't get any ideas here. Okay. So what we did is we take a function that is an algebraic time asymmetric encoding. And this term time asymmetric encoding is something that we took from the paper about VDFs. They introduced this concept. So you take with something that's very fast, you start with something that's very fast in one direction, very slow in the other direction, and it's algebraic in nature. So it's something about multiplications and additions. And that already gives you a discrepancy between the sort of disassembly time and messing up the puzzle, and then the assembly time and the delay. But then we speed things up, because what we do is we apply a Stark to the fast direction, and we get a very succinct and cheaply verified proof of the correctness of the relation between the input and the output. So in particular, the function that we take for creating this puzzle is extremely simple. And again, it's not new here. It comes back for a very long line of suggestions from the Slough construction by Lensta and Veselovsky, and also from the VDF paper. And it has predecessors in other works on delays using cryptography. And it's really using the MIMSI cipher or hash. It just repeats cubing and adding a constant many times, as many times as you need in order to reach your delay. So this is the fast direction is one of repeatedly cubing and adding a constant, because cubing is 2 multiplications, adding a constant is 1 addition, so it's very fast. But if you go in the backwards direction, you need to take a cube root, which roughly takes logarithm of p many multiplications. So 2 multiplications in the forward direction, or 3 operations, because you have 1 addition. But in the backwards direction, in the slow direction, you need to do log of p many iterations, and we take p to be a 256-bit prime. So there's a roughly 128 factor, multiplicative factor between the time it needs to, you compute the fast direction and the time it takes to compute the backward direction. And concretely, it means that if you spend 1 second in creating the time lock, it will take roughly 2 minutes to unlock this thing. Or if you spend 30 seconds locking something, it will take 1 hour to unlock it. And the locking mechanism is extremely simple. It's roughly a 5-line code program. Now, one way to verify is to do naive replay. So once I unlocked the puzzle and I repeatedly computed square roots and reduced the constant and repeated this many times, I can sort of present this, the input to the world, and everyone can do the fast direction, which is similar to locking. But if you look at how much time it would take and how much gas cost it would cost on, let's say, Ethereum, it would be roughly 1 second costs 1 billion gas, because it's roughly 100 million multiplications, and 30 seconds would be 30 billion gas cost, so that's too expensive. So what we do is we apply a Stark, which gives you a very succinct proof that is efficiently verifiable, and we reduce the cost to roughly 10 milliseconds for both of these things. Starks scale very well, and the gas cost is 1 to 2 million gas for both cases, okay? So, and again, this is something that we implemented and is ready for deployment, this one concept that gives you both a time lock and a VDF. Now, just in terms of measurements, these are some numbers that we got. So if you want a 1 second delay, a 1 second locking time that gives you a 2-minute delay, the proving time without a lot of optimizations can be made half a minute. This number can go down if we further optimize it. I want to emphasize that this isn't the delay, so you don't have to wait 2.5 minutes. This is the time the prover takes, and it can be done in parallel to the process of understanding what unlocking the puzzle, okay? And for a delay of 15 minutes, the proving time for us is 3 minutes, and for 1 hour, it's a proving time of 9 minutes. This is the system that we built. Now, the proofs are pretty small in size, between 40 and 70 kilobytes, and the gas cost, you can see it, it's between 1.5 and 2 million gas. So it scales very slowly, okay? Now, I want to mention that there, with a delay function or a time lock, it's very important to know how much time or delay do you get in your function. And there are two potential speedups that we're aware of. The first one is to move to faster hardware for doing the multiplications. So for instance, Kelly Olson from Supranational told us that if someone spends roughly $1 million in 9 months that it will take to generate this thing, you can get a chip that does modular 256-bit multiplication in 1 to 2 nanoseconds. So you can get roughly a 10x improvement in the delay. I just want to say that you could still be in the same. It's okay to use the system. It doesn't, break it or something. You could still. It just means that the delay time that you get is a factor 10 worse in the if such a chip arises. Another thing that one can contemplate is using parallelization, which would give you, you would do an amortized delay. You would basically, instead of finding a root for each iteration, you would compose several of them and in one shot compute a root for several iterations. This could give you potentially a speed up, but it sort of goes down, the ability to get this speed up comes at a very heavy cost because you need a lot of processors and it doesn't scale that well. And the mitigation for both of these kind of things is to sort of change the parameters slightly, which you could do over time or decide that once every, let's say, 3 months or 6 months, you're changing things a little bit. So you could change the modulus, increase it in size. You could move to more variables than one. Instead of using one state variable, you could use 2 or 4. And if you look at the numbers, this very quickly sort of makes each one of these attacks much harder to practically perform. So this is something that could be sustainably used over a large period of time, so we believe. Now, there are other VDFs out there. So for instance, the two popular ones are RSA-based and class group-based. This is a very brief comparison of them. So the Stark-based one is post-quantum secure. The modulus size in bits for our system, as it's currently built, is 256 bits, and you can even reduce this size more, and you would still get a meaningful VDF. The reason this is interesting and important is that it means that you are probably closer in your estimates for the speed of the hardware that is computing the basic operations, the smaller the modulus is. So the larger and the more complicated the basic computation is, the more uncertainty you might have about how efficient is the hardware everyone is using on and what kind of speed ups are lurking out there that no one knows about. So having a smaller modulus is a big advantage. And ours, among the contenders out there, has the smallest one. And you can even make it smaller and still get a meaningful VDF. Our system is transparent, no trusted setup. That is shared also by class groups. Another thing shared by class groups is that both our system and the class groups one is already deployable today. So I learned yesterday that the Chia testnet is already working with the class group-based VDFs, which is a huge achievement. And our system is also ready for deployment. The perhaps most interesting from a developer's point of view thing is that in our construction, and it's the only one where you can get both of these use cases. You can get both a time lock and a delay function for the price of one thing. And I want to give examples about how you might use this as a developer for something meaningful. So let's start with, and let's take concrete numbers. Let's suppose we're working with a time lock of 1 second, which gives you a delay of 2 minutes, and the proving time is roughly half a minute. And let's even assume that actually the proof must be computed after the delay has been the time lock has been unlocked, okay? So suppose you want to run an auction with sealed bids, and you want it to be so that people who are putting in the bids cannot retract their bids, and no one can know what's in the envelopes until the bidding phase has ended. So let's work with a bidding phase of 1 minute. So you want to run this auction maybe for the ENS name server, or maybe it could be Gnosis or any other thing, or Uniswap or any other DeFi contract that wants to run an auction on something. So you could set the bidding phase to be 1 minute long. So the bidding phase starts. I want to put the bid. What I need to do is use my smartphone for 1 second to basically seal my bid, and then I post it. So the bidding phase is 1 minute. It takes me 1 second to seal my bid with very simple computation. So the first bid has been submitted to the blockchain. No one knows what's in there for the next 2 minutes. And the bidding phase ends after 1 minute. Still no one knows what was in my envelope. Now, it takes 2 minutes to unlock the very first bid, and it takes 2 minutes to unlock the very last bid, but after 3 minutes from the starting of the auction, all bids have been unlocked, right? And now we need to generate a Stark proof, and we can actually batch a proof for all of these bids together, and in another half minute for the cost of roughly 2 million gas, you have the, the unsealed, open envelope values along with one proof that attests to the validity of all of them. And you can use this in an auction, tomorrow. For the same, with using the same smart contract, you can also use it in a gaming scenario. And this is now for the VDF version. So in the VDF version, there's no locking because the input to the delay function is going to be the randomness coming from the block header. So someone purchases a card in a game. This could be, a Gods Unchained card. This could be the next CryptoKitty. So you pay the money to get this pack of cards, right? And you want to make sure that when people are purchasing these cards, no one, the miners, they don't really know what's in this pack of cards or what kind of CryptoKitty they're actually getting. So they're going to have to wait for 2 minutes. During these 2 minutes, basically, after the purchase, we take the block header. We compute from it the randomness, which takes 2 minutes. And then by the time that is done, we already know what the randomness is. We need to pay another half a minute in order for a proof, Stark proof, to be generated for this. And then the proof plus the value goes on chain, and now you can distribute the goods. So you can open the loot box, you can get your cards, you can get the CryptoKitty. That's the way you could use this. So we have this one smart contract that could be used both for auctions and for gaming, but there are other applications. You could use the time lock puzzles to prevent front running. You could use it for delayed assured payments, as we said, in many other applications. And the same thing, the VDF has many applications. That's why there's a VDF Alliance and a huge project for it. Of course, most famously, you can use it for better proof-of-stake protocols and sort of reduced electricity mining. You can use this for fair leader election without the ability to influence things, and you can use this for sortition or sort of sampling people and making them part of the governance of your network in a more fair way. So in conclusion, what we talked about was that we have a smart contract that is ready for deployment. You could use it on layer 1, but you could use it also on layer 2. It allows you 2 things for the price of 1. Both time locks and fair randomness. And if you're interested in, working with this smart contract or have ideas how to extend it and use it, then please talk to us. You can first of all come to us here at the conference. We'll be here throughout. You can also send an email to vdf@starkware.co. You can follow us on Twitter. So thank you very much.
Great, thank you. Are there any questions?
I was just wondering, aside from cube and cube root, what other functions and inverses you've considered?
So you can take, so first of all, we're following the footsteps of the VDF paper, and they suggested a large number of rational permutations. So you can take any permutation that is low-degree rational. I mean, you could, so the simplest one of them is cube root, but it could be any root of a pure, just polynomial whose exponent does not divide the order of p minus 1. That's one example. You could use rational permutations, and there's a number of them. And I mean, there's a large space of, there are things called Dixon polynomials, and as long as it's relatively low degree, and it's a permutation rational function, we can work with it. And by the way, all the parameters would be pretty similar. So the proving time, the verification time, the delay time are pretty robust to these.
Thank you. So I did notice that on your slides, you used 1 core for generating the puzzle, but 72 cores and 140 gigabytes for the proof, right?
Yes.
I'm wondering, and that's a criticism that you usually hear about Starks, but I'm wondering, is that something that you can look out for that makes it particularly easy to parallelize that work on the structure of the Stark or something like that?
Great question. So for the delay function, it's very crucial that it is inherently sequential and very hard to parallelize. That's part of the definition part of the requirement of something that would be a good delay function or time lock. So that thing we don't know and we don't believe you can parallelize. Now, Starks are very parallelizable, and that's part of the reason. So the amount of computation that is actually going into proving is much more than this 1 core times 1 second. But you are allowed to parallelize this thing, and indeed Starks and other proof systems are extremely parallelizable, and that's why you get this sort of magic that the proving time is can be made negligible or comparable to the time that it needs to you need to do the sequential computation.
Hi, so I have a question. Since the scalability is very high, but would the delay function cause when you review the trade, then it will take a long time, like I need to wait for 2 minutes until I know is my trade successful or not? Is that a problem? Or how do we solve it?
What, that it takes 2 minutes for the delay to be computed?
Yeah, like you show this 10K trade per second, but does that mean for every trade, I need to wait until it gets revealed and it takes a really long time, right?
Okay, so in the context of scalability and proving that a huge batch of trades settle correctly, we actually prefer to have no delays and no, we don't want to wait any time. And indeed, it's a big computation, we do it, but we try to do it as quickly as possible. I want to say that in the context of what I spoke about today, having a delay of 2 minutes is a feature, it's not a bug. The whole reason, like the D in a VDF, or the time in time lock, is all about generating that delay. And you'll notice that the time that it takes to generate the Stark is negligible compared to the delay. So the delay does not come from the Stark part. It comes from the, this is a feature of the design that is intended to be so, okay? Yeah.
Okay, thank you very much, Eli. So as the next talk, we have Ariel setting up, and he's going to talk about Plonk, one of the 2 really, really important things when you want to design a zero-knowledge proof system. The first one is you got to know about polynomials. Every efficient proof system today basically uses polynomials because of one feature, that 2 polynomials, if they're the same, then they're the same everywhere. If they're different, then they're different almost everywhere. And the other thing that you got to know is how to come up with a good name. And this is how we have names like Plonk and... We're able to write a paper. So, can we make the thing come up? Okay.
Oh, okay. Thank you. So this started as a joint project of Protocol Labs and the Aztec protocol, and now we're developing it, continuing to develop it at Aztec. So a one-line introduction to ZK snarks. So ZK snark allows you to prove that you know some secret W without leaking information on W. And they're also very interesting when you don't care about this leak of information, because the proof that you know W can be much shorter many times than W itself. So those are ZK snarks in a sentence. And for these proof systems to be secure, they require some sort of setup phase before you start proving and verifying. And many times, this setup needs to be what's called a trusted setup. And what that means is that the setup participants have some, if they all share the randomness their computers used during the setup, then they will have the power to forge proofs. So this explains this picture from the first Zcash ceremony, where someone is destroying the computer so that there's no chance the bits of that randomness could ever be discovered, or at least this reduces significantly the chance of retrieving those bits. This setup, as you can see, can be a painful process, in particular for the computer. And what are our options in terms of what setup our SNARK will need? So until 2008, until very recently, it was very much all or nothing. So we had these per circuit setup SNARKs, which means that before starting the setup, you need to decide exactly what sort of statements you want to prove. And two things. So one thing, if it turned out all the setup participants colluded or something went wrong, the setup is worthless. And the second thing, say you want to, I want to make a small change in the type of statements I want to prove, throw away the setup. It's totally worthless. In fact, in Zcash sapling, we decided at some point that we want something in the encoding to be big NDN instead of little NDN in the circuit, or it was the other way around maybe, and we restarted, the sapling setup was restarted after, I think, about a month because of this. So that was one extreme, and the other extreme is the type of things that Ellie is and others by now are also developing, where there is no trusted setup. The setup is basically just picking a hash function that we all agree is secure. But there's no secret trapdoor, there is no collusion of participants. And what's interesting is in the last few years, other proof systems with this property of transparent setup are coming up. So something interesting that started in the very recent years is some sort of non-trivial trade-off in how painful is the setup procedure. And this is sort of where Aztec is concentrating, where we're concentrating our efforts. And this is the topic of today's talk. So this is what's called SNARKs with a universal updatable setup. So what does that mean? It means, yes, you do have a trusted setup where if everybody is corrupt, they can forge proofs. But two things. The setup is universal. So if you change the statement you want to prove, you don't need to redo the setup as long as it's described by a circuit, the statement is described by a circuit of a certain bound that you did fix in advance. And also the setup is what's called updatable. So what that means is, say we were unlucky and up to a certain point in time, all setup participants were corrupt and they shared with each other the secret randomness they used. If at any point, if someone honest comes and contributes more randomness to the setup without leaking this randomness, then from that point on, the setup is successful. The parameters are secure. So Plonk is a SNARK with this type of setup. And let me give you straight away some numbers. So kind of our point is you can have this sort of setup without compromising, and even in some dimensions gaining compared to the best per circuit setup SNARKs. So basically, when the function you're computing has some algebraic structure, like the MIMC hash function, we can even beat Grot 16 in proving time. we can come close in less algebraic functions like SHA-256. And these numbers, this is very much work in progress. And we pay sort of, if you look at the proof lengths, we pay sort of a factor 3.5 in proof length compared to Grot 16. So we have, if you use the Ethereum curve, we have like half kilobyte proofs. If you want to be a little safer against number field sieve attacks, it goes to 600, 700 byte range. Right, so we called the system Plonk because it's short for permutations over Lagrange bases for ecumenical non-interactive arguments of knowledge. But Plonk also happens to be a name of a chain of pubs in London that have miniature golf and video games, and that's where the Aztec team goes to relax after working on Plonk. All right, so let me give you some intuition to how the system works. And I'm going to, because of time, I'm going to skip some parts, and I recommend to search on YouTube Plonk Simons for a version of what's to come with a little more details. So basically, there are two things you need to understand. And the first thing is that, so I didn't go to full screen, sorry. The first thing you need to understand is that basically all you need is a permutation check. And what do I mean by that? So, so how these things works is, we start with we want to prove a statement like this confidential, this Zcash transaction is valid, and we translate it always to a statement about arithmetic circuits. For example, a statement of this form. I want to prove that I know some numbers A, B, and C, such that A plus B times C equals 7, for example. So this type of statement, it's described by this circuit, right? We have this addition gate where A and B go in, and then C joins them in the multiplication gate. So you can think about it, this statement, there are 6 values involved, right? We have these 2 gates, the addition and multiplication gate, and each gate has 3 values, the left wire, the right wire, and the output wire. And now, what do we need to check about these 6 values? So the first thing we need to check is the gate checks. So we need to check for the addition gate that the left plus the right is the output, and for the multiplication gate that the left times the right is the output, is O2. The second thing we need to check is we can call it the wire check or the copy checks. So these 6 values, they're not independent values. If, for example, the output wire of the first gate should equal the left wire of the second gate, right? They're the same thing. So this corresponds to the check O1 equals L2. So here it looks like one small innocent check, but since we're not restricting the fan out of our circuits, this can be a really huge thing. That is, the output of some gate can be the left wire of some arbitrary subset of all the gates, and it can be also at the same time the right wire of some other arbitrary subset of gates. So this the wire checks, the copy checks, can be a big thing. And the third thing we need to check is what's been called in the last few years the public input checks. That, we want to say that the output of the circuit is 7. And what I've tried to convey a little is that the hard part here is the wiring checks. Said differently, if the prover was nice enough to sort of align the left, right, and output values correctly, and we just need to do these coordinate-wise checks of the gates, our job is easy, and the hard part is really these wiring, these copy checks or wire checks. So what I want to show you is that all these copy checks can be compressed to one single, what we can call permutation check. And this idea, the first time at least I saw it, was from a work of Grot in 2009. So think, right, we have the left, right, and output values. Think of writing them all in one long vector. And now we wanted to check that L2 was equal to 01. So if you think about it, that's exactly the same as saying that this vector V is invariant under the permutation that flips the second and fifth location and leaves everything in place. So, right, so this vector V being invariant under this permutation that changes these two places, it's exactly equivalent to L2 equals 01. And now this is just one copy check, but basically however many copy checks you want to enforce among these values, you can take one permutation that does a cycle over each sort of set of values you want to be equal, and then being invariant under this permutation is exactly equivalent to enforcing all these copy checks. All right, so that's sort of the first thing I wanted to sort of convey to you, that the main thing to do is a permutation check. And now the second part is to understand is that permutations are easier to check on multiplicative subgroups. And I'll try to explain exactly what I mean by that. So an important part for us is this work of Bayer and Grot, that, right, this permutation check is sort of like n checks, right? For each location of the vector, you need to check it's mapped to the right thing. And this Bayer-Grot randomization, it will reduce all the permutation check to one product check. So what do I mean by that? I'll give you a simplified example. So suppose we're giving two vectors of length 3, and we want to check that they're the same as sets, meaning that maybe they're in different order, but the elements, ignoring order, B1, B2, B3, and A1, A2, A3 are the same elements. So how can we do such a check very concisely? So here's something you can do. You can choose some random gamma in your field, and now just check the product of all the A's versus the product of all the B's when they're shifted by this gamma. So obviously, if the A's and B's are the same set, then the products will be equal. And what is easy to see from what's called the Schwarz-Zippel lemma is that if they're different as sets, then with high probability over gamma, the products will be different. So this is a way using randomness to check that is one set of permutation, is one vector a permutation of another with just one product check. Now, of course, we don't want to check in the example I showed you that some permutation holds. We want to check that a certain permutation holds for a sigma that we chose. And for simplicity, I won't show you this, but basically what Bayer-Grot do with a little more complex randomization, you can check using one product that whether a specific permutation holds between A and B. Or A and itself. B can be just A. All right, so now for something pretty different, for one slide at least. So we sort of wanted to do this product check. And I want to give you some framework, which is somewhat similar to frameworks that have come up in recent papers like Supersonic and Fractal in Marlin that you'll hear about fractals after me. But I specifically like this framework. I think it lets you design protocols really in a comfortable way. So this is something I call an H-ranged polynomial protocol. So what does such a protocol look like? So we fixed in advance some set of polynomials in the beginning of the protocol. We call these like the pre-processed polynomials. And we also fixed some special subset of our field. And now what does this protocol look like? So we can think, we have some prover, and the prover will just send, you can think of it to some ideal party, some polynomials of degree smaller than D. And we can be sure that if the prover tries to send something else, the whole protocol is aborted. And now, how does the verifier choose to accept or not? At the end of the protocol, the verifier will ask this ideal party, does some polynomial identity hold on H, on this set H, between the polynomials the prover gave me and the pre-processed polynomials? So, right, that's quite abstract, and right, there's a lot here. I'm just assuming the prover there's ideal party, the prover is sending him polynomials of a certain degree, and I can be sure that's what he's doing, and I can check some identity on these polynomials. And the punchline is that using this Katayza-Varucha-Goldberg polynomial commitment scheme, this work introduced this notion, which has become very, very popular, and a lot of works a lot of people are working on this. But basically, using their polynomial commitment scheme, I can take such an abstract protocol and compile it to a protocol where every such message of the prover that was a whole polynomial is in the real compiled protocol is just going to be 32 bytes or 48 bytes, depending what curve you want to use. Okay, and now just a small mathematical two definitions. So we're going to always, the H we're going to work with is a multiplicative subgroup. So what does that mean? It's just a subset of elements of the field that are powers of some alpha, such that alpha to the n is 1. The order of alpha is 1. And we'll use this notation that Li is the I-Lagrange polynomial. So that just means that Li is a polynomial such that Li of alpha to the I is 1. And Li on alpha to the j for other j's is 0. So right. So we were talking about doing a permutation check. In this language of polynomials, what is this going to look like? So we have some permutation sigma on 1 to n. And now P has sent already some polynomial, and he wants to prove that f is invariant under this permutation. Meaning that, what does that mean? That for every I, f at alpha to the I is equal to f at alpha to the sigma I. And I'm going to ask you to believe me that sort of using this Bayer-Grott randomization stuff, we can reduce this to this scenario, that P has sent some 2 polynomials, and I only want to check that the product of F's values on H and the product of G's values on H is the same. So I've done a few big steps here, but let's assume this. All right, so now I want to, using this terminology of an H-range protocol, I want to show you how to check that the product of F's values and G's values are the same. And the point is that using this terminology, it's going to be extremely concise. So what will this protocol look like? So P will compute some sort of auxiliary polynomial Z that accumulates the products. So Z will start at 1, and then at the ith point, it'll be the product of F over G on the first I minus 1 points. And now P will send this polynomial to the ideal party. And what will the verifier check? So the verifier will check this first thing, because of L1 is only non-zero on alpha, it's checking it on H will check that Z really starts from 1. And the second check, which is more the interesting part, Z times F equals Z at alpha X times G. So this really checks that Z is accumulating the values of F over G. And I claim to you that these 2 checks are enough. Why is that? So remember that this group wraps around. Alpha to the n is just 1. So, I made a 1 index. I noticed I made a 1 index mistake here, but no, sorry, this is fine. So what do I know? I know that Z starts from 1. Z is really accumulating the values of F over G. And also, it ends up, since the group wraps around, it ends up at 1. So it means that the product of F over G over H is 1, which exactly means that the product of F's values is equal to the product of G's values. How am I? Do I have like a minute? 2 minutes, thanks. Okay. So that is the core of the Planck protocol. And I want to talk for 1 minute about more recent stuff. So what we noticed while working on this is that really we don't need to think about circuits. We can think about this thing that we call now turbo-Planck programs, where it's sort of an execution trace of a program. And the prover is showing 2 things about that he knows, like a trace like this with two properties. One are that some low degree constraints hold between the rows. This, by the way, this is sort of inspired and similar to things that are happening in Stark research, like what's called the air representation. But the difference is that this permutation check also allows us to do global checks. Like, for example, to check that, say, A100 is equal to D2. So this, and I'll end by saying one more thing. So kind of what we noticed is actually this permutation check was a global check. It's actually, you can think of it as a randomized local constraint. So the verifier chose some random gamma, and then the prover committed to Z, and then really what we checked on Z was a local thing on Z on X compared to Z of X times G. But sort of a local randomized constraint allows you to do a global check. And sort of what we're doing now is seeing what else we can do with these randomized constraints. And we hope to tell you more about that in the coming weeks or months. Yeah, so that's it. Thank you.
I had a quick question. So you showed that the Plonk turns out to have a faster prover on MIMC, but a slower prover on SHA-256 than something like Groth.
Yeah.
Is that thanks to this error-like representation, or what do you think is the reason for that?
So Groth and the QAP stuff works really well when you have a lot of binary values, because the scalar multiplication you're doing is with the actual witness values. So when a lot of them are zeros and ones, your scalar or your group exponentiation is extremely fast. So that's one thing, and we may be able to also change our code to take partial advantage of that, but it's very work in progress, and I'm not sure.
So I was wondering if the size of that group H is on the order of the number of wires in this circuit. Or is it fixed, like in the universal setup?
It's the total number of gates.
On the slide where you talked about where the verification was easier on subgroups, you used this gamma. So you said like with high probability you could verify that two vectors were equivalent under permutations by doing arithmetic in the field. Wouldn't it be possible to do arithmetic in the polynomial ring and get like to know for sure rather than without with the high probability statement?
So I'm not completely sure I follow, but sort of to get really short proofs, you want to only check your identities at one random point.
At one random.
Can you compare and contrast Plonk and Slonk?
Plonk and Slonk?
Yeah.
So Slonk can be efficient if you're... It doesn't have the sort of the part of global constraints, but in circuits that can be sort of represented very locally on a grid, the connections are very close to each other on like a three-dimensional grid, Slonk maybe give faster proving times because the prover doesn't have to work for this permutation argument that enforces the global constraints.
Okay, thank you very much.
Thank you.
So this is a really great session because we get to see sort of a lot of different things from the world of snarks and zero-knowledge proofs. And for the last of the day, we have Nick talking about fractal. And one of the most powerful things maybe that you can do with snarks is something called recursive proofs, where you actually prove that another snark was correct. So I give you a proof of a proof of a proof of a proof. And this is amazing because you can prove that an ever-growing or ever-expanding computation, like a blockchain, is always correct. So I can, always give you, I have your blockchain, and then you get a proof that, you have just the last block, and you know that the entire blockchain and all the transactions are in it correct. And Fractal is the first system that really showed how to actually practically get recursive snarks with post-quantum security. So that would be that it only uses hashes, and it is secure even against, or we hope it's secure even against an adversary that has a quantum computer. So it's very exciting.
Thank you, Benedict, for basically giving my whole talk for me. So this is going to be very short. Here I'm here today, as Benedict said, to talk about fractal and more generally post-quantum recursive snarks, so recursive composition of snarks. So there is one advantage to being the last presenter in the day, which is that I don't have to define what a snark is. So instead, I'm just going to jump directly into what is recursive composition. So recursion is about verifying a snark proof within a snark itself. So what might this look like? Well, let's do an example. So let's say that you have some function f, and you want to verify repeated application of f. So I want to apply f to its own output t times. This I represent by f to the t. And one way I could do this is kind of using Ellie's starks. I could just kind of prove f to the t directly. But what I'm going to do instead is something a bit strange. So I'm going to first prove a single application of f using any snark I like. This will give me an output z1 and a proof pi1. And what I do with that is I then feed it into the snark prover again. And so I prove another application of f. But in addition to that, I also prove that you would have accepted the proof pi1. What this means, this has the cumulative effect of proving that there are kind of two transitions, right? That kind of f of z0 equals z1 and f of z1 is equal to z2. And I can keep doing this over and over again, and I will obtain kind of a series of proofs, and each proof attests to the entire chain kind of backwards through time. So this is a way of proving kind of an iterative computation using only kind of small proof blocks. And one nice advantage of this is that the size of the statement that you're proving is independent of the time t. Notice that kind of what I'm doing here doesn't depend on t. In fact, it depends so little on t that I could even say I don't care what t is. I could say that t is infinity, right? And just keep proving applications of f over and over again. And these intermediate proofs are things that I can spit out, so kind of at any time that I like, and verify at any point. This is kind of a very important feature for things like succinct blockchains, which probably you have heard of. Because a blockchain, you can think about it as being a computation that runs forever and ever, right? You have you assemble some transactions, you put them into a block, and you kind of do this for all eternity. So it is very important to have intermediate verification steps for succinct blockchains, because otherwise, you'd have to wait till the blockchain ends to check anything. Another application of this, basically anywhere that you can use a stark, you can use something like this. So VDFs is a very nice application. In a VDF, you would basically replace this function f with your whatever hash function you like, your cube root function. There are other applications also to kind of decentralize computation, this kind of thing, and possibly many more. Okay, so that's kind of at a high level what recursion is. Now I'm going to talk about kind of the cryptographic foundations of recursion. In particular, what are you actually building when you recurse a snark? So there are kind of two formal definitions of what you're building, so-called incrementally verifiable computation, which is what I had on the previous slide, and a more general version called proof-carrying data, which is kind of, you can think about proof-carrying data as being a generalization of the previous slide to more general graphs. So rather than in the previous slide we had a path, now you can think about a general DAG and kind of accumulating proofs along a DAG. So these are the things that you actually want to build cryptographically. And we know from theory, so this is from 2013, that if you have a snark with a succinct verifier, and it's adaptively secure, then you can recurse it in the sense that you can obtain this proof-carrying data primitive from it using recursion. Moreover, this construction has a bunch of really nice properties. Or rather, it preserves the really nice properties that you started with. So if you have a zero-knowledge snark, then you get zero-knowledge PCD. If you started with something that had a trusted setup, you get the same trusted setup. And if you start with something that has transparent setup, you get transparent setup, and so on. There is one pretty important property that is kind of that was not proved to be preserved by this transformation, though, which is post-quantum security. So let's say that you start with a post-quantum snark, something like Aurora or Starks or something like that, and you recurse it, do you get post-quantum PCD? So this was kind of not addressed back in 2013. And so the first thing that we do in this work is we address this. So we prove that recursion preserves post-quantum security. So this is expressed in this nice diagram. If you start with the post-quantum snark, then you obtain post-quantum PCD. Also in the post-quantum setting, zero knowledge is preserved. And kind of what is the reason that this doesn't immediately follow from this prior result? Basically, what you do in this prior result is that you take your adversary and you immediately make it deterministic. And this helps you kind of do the proof. The way that you do this is you fix its random coins in advance, and there's always a best choice of random coins. In the case of quantum adversaries, there is no such thing as making a quantum adversary deterministic. Like, no matter how hard you try, the quantum adversary can always kind of measure itself and produce more randomness. And so you need to deal with essentially randomized adversaries, like inherently randomized adversaries. And this requires basically some definitional work. You need to come up with a notion of post-quantum knowledge soundness that suffices to do recursion. And moreover, you need to prove that this is like something reasonable that you can do, and so we prove it for our construction that I'll talk about later. Okay, so this is kind of the end of the theory of recursion part. Now I'm going to talk about recursion in practice. So here is a bubble with all of the snarks in it. If your favorite snark is not there, it's represented by these 3 dots. And inside of this bubble of all snarks, there are snarks that have succinct verifiers. Okay, so there are snarks where verification is faster than computation. And what theory tells us is that we can recurse all of these snarks. But this isn't the whole story, because it turns out that in practice, the only snarks that we really know how to recurse efficiently in terms of like being able to run recursive composition on a computer is the ones in the green circle. So there is kind of a gap here between kind of what we theoretically know how to recurse and what we can efficiently recurse. I should mention that kind of there is an outlier which is bulletproofs. So bulletproofs is sort of recursible using some new techniques developed late last year, although it's not recursion in the sense that I'm talking about in this talk, and so we're going to kind of ignore it for now. The question is, in this green circle, what do these snarks have in common? Okay, they're all pairing-based, but is that like the reason why they recurse? And moreover, can I put transparent snarks in this circle? Notice that all of the snarks in this circle are trusted setup snarks. And can I put post-quantum snarks in this circle? So we're going to answer all of these questions during this talk. The first one is, what do these snarks have in common? And the answer is pre-processing. So all of these snarks are what's called a pre-processing snark, which basically says that the verifier is given rather than the full description of the circuit, he's given some cryptographic digest of the circuit. And given this cryptographic digest, he's succinct. So he's kind of runs in time much smaller than the size of the circuit. It turns out that if this is the case, then the cost of proving a recursive step, a single recursive step, remember this kind of this diagram I had with many steps, the cost of proving any single recursive step is essentially the same as the cost of proving the original circuit. So to write that in more kind of symbols and stuff, the time for proving a recursive step, which consists of proving a step and then also a proof, is the same up to a like an additive overhead, a sublinear additive overhead, as the cost of just proving a single step. So why is this interesting? Well, let's compare kind of the original proposal for doing recursion. This is due to BCCT. So this is a little bit complicated, but basically what they're doing is they are using a snark for machine relation. So this is like the bounded halting problem relation. So the instances of this relation are descriptions of machines, like Turing machines, programs, along with inputs and time bounds. And you take the description of the machine, you like run that machine, and you check whether it outputs 1 in t steps. Then what you do is you construct your recursion algorithm, and the recursion algorithm takes in a description of the machine along with some other stuff, and it checks that the transition was correct and that the verifier accepts on this machine description. And then you take the kind of weird recursion step of proving that this recursion machine R applied to its own description accepts. So this is how you do recursion in the machine setting. And basically what you have to do here, because you're taking R and you're plugging in a description of itself, you have to do some kind of universal simulation. So there is a universal machine that, given a description of a machine, runs that machine. Doing so incurs some overhead in the cost of just running the machine. You can kind of think about it like a virtual machine or something like this. This incurs some kind of per instruction overhead, which is not just a multiplicative factor 1, but something greater. And this is kind of what prevents you from practically realizing preprocessing in this way. Okay. So given all of this, what we want to obtain in order to do this post-quantum PCD, given the two theorems that we have so far, is a post-quantum preprocessing snark. And lucky for us, there is one. So there exists a post-quantum preprocessing snark for the R1CS problem, which is also transparent. In particular, or rather, both of these properties are implied by unconditional security in the quantum random oracle model. And why is this kind of exciting? Basically, all prior constructions of preprocessing snarks have both of these drawbacks. They are all pre-quantum, and they all require trusted setup. So this is the first construction achieving either of these things, achieving either post-quantum or transparent setup. In more detail, our construction is called fractal. We kind of present some asymptotic numbers. So not only does there exist a preprocessing snark, but it's also reasonably efficient. So the time for preprocessing and proving is roughly n log n, basically FFTs. The time for verification is polylogarithmic. And the proof size is also polylogarithmic. In terms of like concrete numbers, you're basically looking at the order of minutes for proving a circuit of something like 2 million gates. And the verifier time is on the order of milliseconds. Proof size ranges between 100 and 250 kilobytes for things that we are able to prove. And one interesting thing to note is that asymptotically, this matches the performance of the best non-preprocessing post-quantum snarks. So kind of you're not really paying very much for preprocessing, at least in the asymptotic setting. Okay. So let's kind of dig a bit more into the concrete costs of fractal. So should note that here the random oracle is being instantiated using the hash function Blake. So this is a graph of comparing the fractal verifier to different verifiers for different snarks. As you can see, it kind of closely matches the time for Marlin, and Gross16 is a little bit lower, but it's kind of the same order of growth. The green line is Aurora, which has a linear time verifier, so you can see the enormous difference in terms of verification time. Then proof size. So here we just have fractal and Aurora, but this is because kind of the proof size for Gross16 would not be visible on this graph. But you can see that kind of fractal and Aurora, the proof sizes are roughly the same, and they have the same order of growth. Now the proof of time. So this also sits like somewhere nicely close to other comparable snarks. So all of these are asymptotically n log n. Fractal is kind of in the middle, it's the black line. Essentially the proof of times for all of these things are quite comparable. Okay, So back to kind of a little bit of theory. So how do you build post-quantum PCD based on this thing? So you start with our construction of a fractal of a pre-processing post-quantum SNARK. This is secure in the quantum random oracle model. Then you have to do a heuristic step. So you have to take the random oracle and turn it into a URS. So I'll talk about that in just a second. This gives you now a heuristic, kind of a candidate construction of a pre-processing post-quantum SNARK with a uniform reference string. So this is the transparent setup part. And then you apply the post-quantum recursion theorem, and this gives you PCD with a URS. Okay. So what is this heuristic? This is the standard kind of random oracle heuristic. So anything that you prove secure in the random oracle model, when you come to turn it into a real scheme, you have to use this heuristic. Basically, this says that a scheme that is secure in the random oracle model, if you replace the random oracle with a sufficiently strong hash function like SHA-3 or Blake or something like that, then it remains secure, and certain security properties that you had in the random oracle model, you keep. This is used pretty much everywhere, so it's not used in Groth 16, but it is used in Sonic, Marlin, Planck, bulletproofs, and Starks, Starkware type Starks. Okay, and so what do we get after all of this mess? We get the first PCD construction with any of the following things. Post-quantum security, transparent setup, and kind of more subtly, this construction supports arithmetic over any large enough, smooth enough field. So this point is kind of maybe a little bit specialized, but if anyone who works with recursion knows, other PCD constructions, other recursive composition, place some strong conditions on the choice of field. And this construction allows you much more freedom in your choice of field. Okay. All right. So now I'm going to do a little bit of the kind of evaluation of fractal, like how recursion actually looks in practice. So to recurse, we need to express the verifier in a language the SNARK understands, right? So we're going to put the verifier inside of the SNARK. This means that we need to convert it into something that the SNARK can prove statements about. So this actually causes some interesting things to happen. So things that kind of you wouldn't think about when you're just proving a single thing turn out to be extremely important when you're doing recursive composition. So this is kind of where these pairing-friendly cycles come from, if you're familiar with that. In our case, the fractal verifier consists of two parts conceptually. There's like an algebraic part and there's like a cryptographic part, basically a bunch of hashes. And when you run the fractal verifier on your computer, these things are roughly balanced. Like the algebra and the hashes cost about the same. When you come to recurse the fractal verifier, this happens. So now the hashes are massively dominant in terms of the cost as a constraint system. So once you convert the fractal verifier into a rank 1 constraint system, the algebra is very, very cheap. This is basically because it's native to the language that we're using, and the hashes are super expensive. So this kind of brings in some considerations about what kind of hash you're going to use. So one thing you could think of doing, the natural thing to do, is to choose like some very well-studied hash families. So like Blake 2 or SHA-3, something like this. So these are very fast. Like per hash, it's about 200 nanoseconds on your laptop. But the number of constraints per hash is quite large. It's about 20,000 constraints per hash, which means that if you implement the fractal verifier using Blake 2 or SHA-3, you'll get something that is of size something like 2 to the 28 constraints. So that's kind of big, and we'd like to bring that down. And so one thing that you do is you can use these algebraic hash functions or Stark-friendly hash functions. So examples of these are Poseidon, Rescue, MIMC, etc. So the time to run the hash on your computer is about 50 times slower. So that these are just not as efficient as Blake 2 and SHA-3, but the number of constraints per hash is something like 300. So it's about 70 times smaller than the number of constraints that you need to represent Blake 2 or SHA-3, which means that the verified constraint system is some order of magnitude smaller. And this actually puts it kind of inside of the realm of practicality. So we aren't able to prove instances like statements of size 2 to the 28, but we can prove statements of size 2 to the 21. So this is very, very necessary. So kind of okay, we kind of lose a bit in terms of the amount of time it takes to actually evaluate the hashes, but doing this step is necessary in order to actually realize recursion. So as a general rule, kind of the cost of recursion comes from doing cryptography inside of the SNARK. So this is like a non-black box use of cryptography. Okay. So now we're going to look at Fractal as a recursive SNARK, kind of the real costs of doing recursion. So here we're going to choose the Poseidon hash function to play the role of the random oracle. And this is the graph that you get. So on the x and y axis, we have like numbers of constraints. And the black line represents how big the verifier is when it is checking the number of constraints that is depicted that is given on the x-axis. Right? So as you can see, this does not grow as fast as y equals x, which is kind of the break-even point. And this blue region is the feasible region for recursion. So this means that after this point, you can start doing recursion because the verifier will fit inside of itself. And this gap kind of tells you how much additional computation besides the verifier you can fit inside of the verifier. So for example, let's say that you're here, you have a circuit C of size roughly 6 million. Then the kind of size of the recursive instance is about 8 million. And given that kind of this circuit size grows very slowly, you can basically say that the size of the recursive circuit for any circuit C is roughly the size of C plus about 2 million. So just a warning, this graph represents an unoptimized proof of concept implementation. So there are many, many things that we can do to optimize things. One thing that is particularly bad is that the prover becomes 10 times slower because we use algebraic hashes rather than kind of more standard hashes. And optimizations are currently in the works that yield significant speedups. Okay, all right. So because I have 2 minutes, I am kind of going to go very, very quickly through things about kind of constructing Fractal. So the basic idea to construct Fractal is the same as the idea to construct every other type of SNARK. You start with some information theoretic proof system, you add a cryptographic compiler, and you get a SNARK. In this case, obviously, you're going to want a post-quantum cryptographic compiler. But in order to get the preprocessing property, you need a certain property of the proof system you start with, which is that it is holographic. So I will talk about that in a moment. What is a holographic proof? So a holographic proof is a proof system. So let's start with a particular type of proof system, a probabilistically checkable proof. You might have seen this before. Basically, you have a proof string, and the prover provides the proof string. The verifier can kind of query into it. So in this case, notice that the verifier's time is at least the size of this circuit. So here I'm checking circuit satisfiability. So the verifier's time is at least the size of the circuit because the circuit is part of its input. A holographic verifier, on the other hand, has access to an error-tolerant encoding of the circuit. So what this means is that I have some other algorithm the index algorithm, that outputs an encoding of this circuit. And the verifier can make queries into this encoding. So definitely the time that is required for doing the encoding is at least the size of the circuit, but the time of verification can now be much smaller because the verifier doesn't actually need to kind of read the whole circuit by itself. So holography, I won't have time to go into this, but holography basically implies pre-processing via a sequence of transformations. Basically what you do is you apply the Macaulay transformation to produce a holographic snark. This works because the Macaulay transformation is black box with respect to the verifier. And then you use Merkle trees to take the encoded input and compress it into a cryptographic digest. Okay. So I'm going to skip this stuff because of time. This is, if you're interested in kind of how you do holography, you can talk to me afterwards. So in summary, we have 3 theorems. Post-quantum recursion implies PCD. Pre-processing implies efficient recursion. Fractal is pre-processing snark that is post-quantum. And so you combine all of these together, you get a construction of efficient post-quantum PCD. And we have implementations of fractal as both a pre-processing snark by itself and as a recursive snark using algebraic hashes. Thank you very much.
Thank you very much. Are there any questions? Okay, then I think that's it for the first day. Thank you very much. It's not quite it actually. There's a reception outside where there's food and drinks, and I hope you come hang out, ask your questions in person to the speakers, and come back tomorrow. Thanks.